Space-time at the widest scale that instruments can probe is treated as a single connected setting in which distance and duration are inseparable parts of one geometry. It is not taken as a rigid container that stays the same while matter moves inside it. The measures that define length and time depend on the shape of this geometry, and that shape depends on what the universe contains. The evidence for this intertwined picture begins with light. Distant galaxies show a systematic shift of their spectral features toward longer wavelengths, and the shift grows on average with distance. To speak of expansion is to describe how large-scale separations change when the universe is averaged over immense volumes. In that averaged description, galaxies that are not locked together in a bound group tend on the whole to grow farther apart as cosmic time advances. This statement is not made about the interior of a galaxy where gravity holds stars and gas in orbit, or about systems where electromagnetic forces set stable size. Expansion is a property of the large-scale geometry used to describe what remains when smaller structures are smoothed away. This wide view relies on a practical assumption. When averaged over sufficiently large volumes, the universe looks roughly the same in all directions and at all locations. It is not a claim that every region is identical, and it does not deny the presence of clusters, filaments, and voids. It is a claim about statistical sameness once the view is widened beyond the largest gravitationally bound structures. Under this approximation, the geometry can be written so that a single scale factor sets the overall size of spatial separations, while time is tracked by a common cosmic coordinate. The scale factor increases as the universe expands, and the increase is read through observations that connect redshift to distance. Redshift is often misread because everyday experience ties a change in wavelength to motion through space, as with a moving siren. For nearby galaxies, the redshift can be described in a way that resembles an ordinary Doppler shift, and this can be a useful approximation. For very distant galaxies, the dominant interpretation is geometric. As light travels across an expanding space-time, the wavelength is stretched along the path. The light is emitted with one wavelength and arrives with a longer one because the spatial part of the metric changes between emission and detection. This stretching influences what telescopes record in several linked ways. A longer wavelength means lower energy per photon. The expansion also spreads the arrival of photons over a longer interval of time, reducing the arrival rate. Together with the geometric spreading of light, these effects make distant objects appear dimmer than they would in a static setting, and the detailed relationship between distance, redshift, and brightness becomes a test of the large-scale geometry. The history of expansion is not captured by a single unchanging number. Observers define an expansion rate that can vary with time, describing how quickly the scale factor grows at different epochs. Because light takes time to travel, redshift also serves as a rough clock with higher redshift corresponding to earlier times. Astronomers connect redshift to distance using several independent methods and compare them to test whether one expansion history can explain the data. At this outer scale, a common misreading is to picture expansion as an explosion that throws galaxies outward from a central point into pre-existing emptiness. The large-scale evidence does not single out a center, and the relativistic description does not require an edge or an outside space. In the homogeneous picture, every observer who moves with the average expansion can describe distant galaxies as receding, and the broad pattern is similar from each such location. The expansion is a property of the metric that sets the rules for how distances are measured between widely separated events. Another misreading comes from treating recession as ordinary speed. Relativity limits local motion through nearby space, but over vast distances, the change of proper distance between comoving locations can exceed the speed of light without any object locally outrunning light. At the largest scales, the finite speed of light and the finite age of the observable universe introduce horizons. One horizon is observational. There is a maximum distance from which light has had time to reach an observer since the universe became transparent enough for photons to travel freely. This limit defines the observable universe as a sphere of information rather than a border of existence. Beyond it there may be more space and more matter, but signals from those regions have not reached the present. A horizon is not a wall. It is a statement about what can influence what given a particular expansion history and a finite signal speed. If late-time expansion continues in an accelerating way for long enough, there can also be regions whose signals will never reach a given observer, even as cosmic time advances without bound. This is a claim about causality in a particular geometry, not a claim about an edge of space. Large-scale measurements depend on how light moves through space-time. In the language of relativity, light follows null geodesics, the paths that represent natural signal propagation in the geometry. In an expanding universe, these paths connect redshift travel time and distance in a way that shapes what telescopes record. The same geometry that stretches wavelength also affects the relationship between time intervals at emission and detection, so the observed rates of distant processes can appear slowed in a predictable way when compared at equal redshift. Within general relativity, the relationship between matter and geometry is expressed by field equations that connect curvature with energy and momentum. In the large-scale homogeneous approximation, this becomes a relationship between the expansion rate and the average energy density of the universe. Different components evolve differently as the universe grows. Radiation thins rapidly because its energy density drops as volume increases and because redshift lowers photon energy. Non-relativistic matter thins mainly with volume. A component with nearly constant energy density does not dilute in the same way, and its growing relative importance at late times is associated with accelerated expansion in the standard picture. The phrase fabric is often used for space-time because it suggests something that can bend and change, but it can mislead if taken as literal material. A fabric brings to mind threads and a substance embedded in a larger room. The relativistic description allows the metric to vary and to carry travelling disturbances known as gravitational waves, yet these are not ripples of a medium moving through an external space. They are changes in the relations that define distance and time between nearby events, and at the largest scales, the dominant change is the smooth evolution captured by the scale factor. Even the notion of time can be misread in this outermost region. Cosmological models often use a coordinate called cosmic time chosen so that it matches the proper time measured by observers who move with the average expansion and see the universe as nearly uniform. This coordinate is convenient for describing the large-scale history, but it is tied to the symmetry of the model, not a universal clock imposed on every circumstance. Local motions and local gravitational fields still produce differences in measured time, but in the large-scale average, the cosmic time coordinate provides a stable way to describe how the universe as a whole changes. From this widest perspective, space-time is read through patterns in light and in the distribution of galaxies across immense distances. The expanding universe description encodes those patterns without adding a center, an edge, or an outside. Persistent misreadings come from importing everyday images of motion through a fixed stage, or of growth into surrounding emptiness. At cosmic scale, the stage is part of the dynamics, and the measurements used to describe it are inseparable from the geometry that the universe itself provides. The large-scale geometry of space-time is not inferred from a single observation, but from a set of linked measurements that test whether one coherent shape can account for how distances, angles, times, and energies appear across the sky. At this outer region, geometry is treated as an average property, smoothing away the clumpy details of stars, gas clouds, and even individual galaxies. The reason for this smoothing is practical. General relativity describes gravity as curvature of space-time caused by energy and momentum, yet solving the full equations for every star and every dark halo is not possible in a direct way for the entire observable cosmos. Instead, the universe is modelled as a fluid at very large scales with an average density and pressure that vary slowly from one vast region to another. Under the assumption that the universe is statistically similar in all directions and at all locations when viewed broadly enough, the simplest family of geometries is selected. In that family, the spatial part of the metric at a given cosmic time can be flat, positively curved, or negatively curved, meaning that the rules of geometry for large triangles and large circles differ from those of Euclidean space. These curvature options are not about bending into a higher dimension in a visual sense. They are statements about how distance relates to angle and area within the space itself. If the spatial geometry is positively curved, the sum of the angles of a very large triangle exceeds 180 degrees, and the area of a circle grows more slowly with radius than in flat space. If the geometry is negatively curved, the triangle sum is less than 180 degrees, and the circle area in this area grows more quickly. In a perfectly flat geometry familiar, Euclidean relations hold, though the overall scale can still change with time through expansion. A central misreading at this level is to think that curvature is only a local feature near massive objects like the space-time around a star. Local curvature is real and measurable, but there can also be a global spatial curvature that describes the average shape of the universe on the largest scales. The two ideas are related through the same equations, yet they play different roles. Local curvature arises from local concentrations of mass and energy, while global curvature is an attribute of the homogeneous solution used to describe the average cosmos. Observers test global curvature by comparing different ways of measuring distance. One way uses standard candles objects of known intrinsic brightness to infer how far away they are from their apparent brightness after correcting for known effects. Another uses standard rulers objects or patterns of known physical size to infer distance from their observed angular size. In an expanding universe, a standard ruler can appear to shrink with distance, and then beyond a certain redshift range appear to grow in angular size again because of the way light paths and expansion combine. The exact behavior depends on the curvature and on the expansion history. A consistent geometry must match these relationships across many redshifts. The idea of a standard ruler is subtle, because nothing is perfectly standard without calibration. What matters is that there exist patterns whose characteristic scale is set by early universe physics that is understood well enough to serve as a measuring stick. A particularly important one is a characteristic separation imprinted in the distribution of matter by sound waves in the hot early plasma later seen as a preferred scale in the clustering of galaxies. When that scale is measured across the sky, it provides a powerful constraint on the geometry because it ties together angles, redshifts, and distances. Another important set of tests comes from the cosmic microwave background, the faint relic radiation that fills space. Its tiny temperature variations form a pattern of hot and cold spots, with a typical angular scale that depends on the size of the sound horizon at the time the radiation last scattered strongly, and on the geometry that light travels through on its way to telescopes. If the spatial geometry is positively curved, that scale is projected onto the sky in a way that makes the features appear larger. If the geometry is negatively curved, the features appear smaller. When this is combined with independent measures of expansion history, a consistent picture can be built. Even in this outer region, uncertainty is handled carefully. Measurements carry statistical errors, and systematic uncertainties and model assumptions can couple parameters so that different combinations fit the same data. The standard cosmological model uses a small set of parameters to describe the contents and geometry of the universe, and current evidence strongly favors a universe that is very close to spatially flat on the largest scales, though the constraint is not an absolute proof of perfect flatness. What is meant is that any global curvature radius, if non-zero, is larger than the observable region by a significant factor within the uncertainties of current measurements. Another persistent misreading arises from treating the chosen cosmological metric as a claim that the universe must be smooth. The observed universe is not smooth at the scales of clusters and galaxies. The smoothness is an averaging statement that becomes better as the scale grows. The geometry used in cosmology is therefore a background, and the real universe is described as that background plus perturbations, small variations in density, velocity, and gravitational potential that grow over time to form the large-scale structure seen today. In this framework, it becomes possible to connect geometry to growth. If the universe contains only ordinary matter and radiation, the expansion history and the growth of structure follow a particular pattern. If an additional component drives late-time acceleration, it changes how quickly density variations grow. Thus, geometry is read not only through distance and angle relationships, but also through the statistics of clustering and the way that clustering evolves with redshift. Gravitational lensing provides another window on geometry that stays within this broad region. Large-scale structures deflect light, slightly distorting the shapes of distant galaxies in coherent patterns. By measuring these patterns across the sky, observers can infer the distribution of matter and test the underlying geometry, because the strength of lensing depends on the distances between observer lens and source, and those distances depend on the metric. In this way, geometry is checked against matter in two directions. Matter shapes the geometry, and geometry governs how matter's effects on light are projected to us. The language used to describe these links can mislead if taken too literally. Phrases like space is expanding or curvature is positive can be heard as statements about a surface in a larger room. The mathematics does not require such an embedding. It uses an internal description in which the metric defines distances and times between neighbouring events. Curvature is an intrinsic property of that metric, measurable by how shapes and geodesics behave without reference to an external space. At this outer scale, another common misreading is to assume that the expansion directly pulls bound systems apart. In the averaged cosmological description, expansion changes the proper distance between commoving points that follow the smooth flow, but bound structures are not commoving in that sense. Their internal gravitational dynamics dominate, and they decouple from the background expansion. The metric that describes the universe as a whole, and the metric that best describes a small region around a massive object, are related, but they are not used in a naive way. by simply inserting a planet into an expanding grid. The separation of scales matters. The outer region is about the background geometry that becomes visible only when distances are enormous and times are cosmological. When these distinctions are kept clear, the large-scale geometry becomes a disciplined reading of the universe that avoids picturing expansion as motion through a static arena, avoids imagining curvature as a bend into an outside, and instead treats geometry as the measurable set of relations that link angles, distances, redshifts, and the growth of structure across the sky. The next step inward, still at a scale that remains cosmic rather than local, is to consider a signal that does not come from discrete galaxies at all, but from space itself, filled with a nearly uniform glow. The cosmic microwave background is electromagnetic radiation that reaches telescopes from all directions, with a spectrum that is extremely close to that of a thermal source, meaning it matches the distribution expected from matter and radiation that once shared a common temperature. Its present temperature is only a few degrees above absolute zero, and it is remarkably uniform. The tiny departures from uniformity at the level of tens of microkelvin carry information about the state of the universe at a very early time, long before galaxies form. This relic light is often misread as a picture of a distant surface floating in space. It is more accurate to treat it as a snapshot of conditions at an early epoch seen by looking far away, because far away is also long ago. In the standard cosmological account, the early universe is hot and dense enough that matter is ionized, meaning electrons and atomic nuclei are not bound into neutral atoms. In such a plasma, photons scatter frequently from free electrons. Light cannot travel freely over large distances because it is constantly redirected, and the universe is effectively opaque. As expansion proceeds, the average temperature drops. Eventually, electrons can combine with nuclei to form neutral atoms, a process known as recombination in historical usage, though it is really the first widespread formation of neutral hydrogen and helium. When this happens, the number of free electrons falls sharply, scattering, becomes rare, and photons begin to stream nearly freely. The cosmic microwave background is the light released at this transition stretched by subsequent expansion from visible or infrared wavelengths into microwave wavelengths. Because this release happens throughout space, each observer sees the radiation coming from a sphere around them defined by the distance light has travelled since that moment. This sphere is called the surface of last scattering, though it is not a solid surface, and it has a finite thickness in time because the transition is gradual. The background's near uniformity shows that the early universe is very close to uniform in density and temperature, but not perfectly yet. The small variations are crucial. They represent slight differences in the density and gravitational potential of the plasma at that early time. These differences seed the later growth of structure. A useful way to read them is to decompose the sky pattern into angular scales from very broad features spanning large portions of the sky to fine features spanning small angles. The relative strength of these scales forms a spectrum that can be measured with high precision. The positions and heights of features in this spectrum reflect several linked physical processes. One process is acoustic oscillation. In the early plasma regions with slightly higher density have stronger gravity pulling matter inward. At the same time, radiation pressure resists compression. The competition sets up oscillations like sound waves in the coupled matter and radiation fluid. These waves have a characteristic distance they can travel before the time of last scattering known as the sound horizon. At last scattering, the state of these oscillations is imprinted as peaks and troughs in the background temperature pattern. Another process is gravitational redshift and blue shift as photons climb out of or fall into potential wells, contributing to temperature differences. There is also diffusion damping, where small-scale variations are smoothed, because photons can random walk out of tiny overdense regions before decoupling is complete. In addition to temperature, the background light is slightly polarized, and the pattern of polarization provides another set of constraints on early universe conditions and later interactions. This is still an outer region description because it is about the universe as a whole, but it is more specific than the general geometry of Section 2, because it ties the geometry to a physical time in the early universe and to microphysics that can be tested in laboratories and in astrophysical settings. The background is also a sensitive probe of the large-scale geometry discussed earlier. The characteristic angular size of the sound horizon depends on the physical size of that horizon, and on the distance to last scattering, and that distance depends on expansion history and curvature. A geometry that is too positively curved or too negatively curved shifts the expected angular scale of the peaks. Because the physical scale is set by early universe physics, matching the observed peak positions becomes a strict check on the metric. At the same time, the heights of the peaks depend on the relative amounts of baryonic matter, meaning ordinary matter, made of protons and neutrons, and non-baryonic dark matter, which interacts primarily through gravity. Baryons add inertia to the oscillations and change the pattern of compressions and rarefactions, leaving a distinct signature in the peak heights. Dark matter contributes gravitational potential without coupling to photons, shaping how the oscillations evolve. Thus, the background is a joint measurement of geometry and content. A common misreading is to treat the background as proof that the universe begins with a singular point that is directly observed. The background does not show an initial singularity. It shows conditions at the time of last scattering, when the universe is already many hundreds of thousands of years old. The description of earlier times is inferred by combining the background with other observations and with physical theory. Another misreading is to imagine that the background is perfectly smooth, implying an early universe with no structure. The measured anisotropies demonstrate the opposite. The early universe contains small variations that later grow. Yet another misreading is to think that the background proves that space-time itself is a substance that glows. The radiation is carried by photons and its behavior follows the geometry, but it is not the metric itself emitting light. The background also reveals motion. The most prominent anisotropy is a dipole pattern, with the sky slightly warmer in one direction and slightly cooler in the opposite direction. This is understood as a Doppler effect due to the motion of the observer relative to the average rest frame of the background. By removing this dipole, astronomers define a frame in which the background is on average isotropic. This frame is often misread as an absolute frame that violates relativity. It is not an absolute frame in the sense of fundamental physics. It is a convenient reference tied to the distribution of matter and radiation in the universe. Relativity allows such a preferred frame to exist as a feature of a particular physical situation, without elevating it to a universal law. In addition, the background can be altered after last scattering. As the universe evolves, photons travel through changing gravitational potentials caused by growing structures. If those potentials evolve over time, photons can gain or lose energy in a net way, producing additional anisotropy on large angular scales. Photons can also be deflected by gravitational lensing, slightly smoothing and distorting the pattern, and this lensing effect can be reconstructed to infer the distribution of matter integrated along the line of sight. At later times, some photons scatter again from free electrons produced by the first luminous objects that reionize into galactic gas, leaving subtle imprints in polarization. These layered effects mean that the background is not only a message from the time of last scattering, but also a record of the space-time and matter it passes through. Even with its precision, the background contains anomalies and open questions that must be handled without overreach. For example, the largest angular scales are limited by cosmic variance, meaning there are only a few independent modes on the sky at those scales, so statistical uncertainty is unavoidable. Some reported features such as unusual alignments or power deficits on very large scales have been discussed for years, but their significance remains debated because of these statistical limits, and because of the risk of a posteriori selection, where patterns are noticed after looking at the data. A disciplined reading treats these as topics of investigation rather than decisive clues. The background also connects to a central tension in modern cosmology. Different methods of measuring the current expansion rate can yield values that do not fully agree within stated uncertainties. The background interpreted within the standard model implies one value while direct distance ladder methods can imply another. Whether this tension points to unaccounted systematics, new physics, or a combination is not yet settled, and the background alone does not dictate a single interpretation without the broader context of all data sets. Within the constraints of what is firmly established, the cosmic microwave background remains a cornerstone because it ties the large-scale geometry of space-time to a concrete early epoch, fixes a set of characteristic scales, and provides an internal consistency check across many independent features. It is a reminder that the outer universe is not read only through bright galaxies and their redshifts, but also through a faint, nearly uniform bath of photons whose tiny variations encode how space-time and matter behave when the universe is still young, and the seeds of later structure are still small. The large-scale picture becomes more textured when the distribution of matter is considered not as a smooth fluid alone, but as a network of concentrations and emptier regions that span hundreds of millions of light-years. This web-like pattern is traced by galaxies, by hot gas visible in X-rays, and by gravitational lensing that reveals mass whether it shines or not. Galaxy clusters are the most massive gravitationally bound structures in the universe, containing hundreds to thousands of galaxies, vast reservoirs of hot ionized gas, and a dominant share of mass in dark matter. Voids are large regions where the density of galaxies is far below the cosmic average, often tens of millions of light-years across or more. Filaments connect clusters and skirt voids, creating a cosmic web. In this outer region, space-time is still treated in an averaged way, but the averaging is no longer perfectly uniform. The aim is to understand how the smooth background geometry interacts with these large inhomogeneities and how the curvature associated with mass concentrations subtly modifies the paths of light and the flow of time across vast distances. A common misreading is to imagine that clusters and voids are simply decorations painted onto an otherwise unaffected expanding space, as if the background expansion and the local gravity can be cleanly separated everywhere. In reality, the presence of inhomogeneities means the metric is not exactly the simple homogeneous form at all points. The homogeneous metric is a background approximation, and clusters and voids correspond to perturbations in density and gravitational potential that grow from small initial variations. In the early universe, the variations are tiny and linear. Perturbation theory describes their growth well. As time passes, gravity amplifies them, and the densest regions become nonlinear, forming halos and clusters. The curvature associated with these structures is still weak on many scales, meaning gravity is not so strong that space-time is wildly distorted, but it is enough to deflect light shift frequencies and alter the rate at which clocks tick in different environments. The formation of clusters begins with dark matter because it dominates the mass and does not feel radiation pressure. Dark matter collapses under its own gravity into halos. Ordinary matter falls into these potential wells, heats through shocks, and forms the hot intracluster medium. The gas temperature can reach tens of millions of degrees Celsius, and because it is ionized, it emits X-rays. This hot gas also interacts with the cosmic microwave background through inverse Compton, shifting the energies of background photons slightly, and creating a measurable imprint known as the Sunyaev-Zeldovich effect. Because this imprint depends on the integrated pressure of the gas, and is relatively insensitive to distance in a specific way, it provides a method to find clusters across a wide range of redshifts. These observational handles allow clusters to be counted and weighed, and their abundance as a function of time becomes a test of cosmological parameters because cluster formation depends on both the expansion history and the growth of structure. A universe that expands faster at late times tends to slow the growth of clusters by stretching space-time and reducing the time available for gravity to pull matter together. In this way, clusters are not only objects in space, but also markers that encode how space-time evolves. Voids offer a complementary view. In a void, matter density is low, and the gravitational potential is shallower. Light passing through voids can experience different integrated effects than light passing through clusters. Over cosmic time, if the gravitational potentials associated with structures change, photons can gain or lose energy in a net way as they traverse them. This effect is subtle, but contributes to correlations between galaxy maps and microwave background anisotropies. Voids also expand relative to the average, because their underdensity means there is less gravity to slow the local expansion of the region compared with denser surroundings. This can be misread as voids being torn open by expansion, but the correct picture is that underdense regions have a different local expansion rate within the overall evolving universe. The cosmic web, with its mix of overdense and underdense regions, therefore represents a pattern of slightly different space-time evolutions laid on top of the global expansion. One of the most direct probes of how these structures curve space-time is gravitational lensing. When light from a distant galaxy passes near a massive cluster, its path is bent. In strong lensing, this can produce multiple images, arcs or rings. In weak lensing, the distortion is small for any individual source, but coherent over large sky regions, producing measurable correlations in galaxy shapes. Lensing is often misread as light being pulled sideways by a force in the Newtonian sense. In general, relativity light follows geodesics, and the bending reflects the curvature of space-time caused by mass and energy. In many astrophysical settings, the Newtonian gravitational potential provides a good approximation, but the geometric interpretation is more general. Because lensing depends on total mass, it reveals dark matter distributions that are otherwise invisible. In clusters, lensing maps show that most mass resides in extended halos, rather than in the luminous galaxies. This supports the view that dark matter is a real component rather than a small correction. It also provides constraints on alternative gravity theories because any theory must reproduce the lensing patterns along with the dynamics of galaxies and gas. Within the standard framework, the lensing signal across cosmic time becomes another route to test the growth of structure and thus the evolution of space-time. Another large-scale effect is peculiar velocity, the motion of galaxies relative to the smooth expansion flow. Galaxies fall toward overdense regions and flow out of underdense regions, creating velocity fields that distort the observed clustering pattern in redshift space. These distortions can be analyzed to infer the rate at which structures grow. Growth in turn depends on how matter responds to gravity in the given spacetime. If gravity behaves exactly as general relativity predicts on these scales, and if the energy components evolve as in the standard model, then growth follows a particular curve. Deviations could signal new physics, but they can also come from observational systematics or from complex astrophysical effects, so claims require careful cross-checks. At this scale, one more misreading concerns averaging itself. It might seem that if the universe is clumpy, then averaging over clumps must always reproduce the same dynamics as a perfectly smooth model with the same mean density. In general relativity, averaging is subtle because the equations are nonlinear. The average of a solution is not necessarily a solution with averaged inputs. This raises the question of back reaction, the possibility that inhomogeneities could influence the average expansion in a measurable way. Most analyses within the standard cosmological model treat back reaction as small, and many studies suggest it is unlikely to mimic the observed acceleration at late times, but the topic is technically challenging and remains an area where careful work continues. A disciplined reading acknowledges the issue without turning it into a broad claim that the entire cosmological inference is invalid. Instead, it treats it as a refinement of how the background plus perturbations description is applied and tested. The space-time across clusters and voids also affects time in a subtle way. In denser regions, gravitational time dilation means that clocks deeper in potential wells tick slightly more slowly, relative to clocks in emptier regions when compared through appropriate signal exchange. The effect across cosmic structures is real but small, and it is not usually measured directly by comparing clocks placed in clusters and voids. Yet it enters through the gravitational redshift of light leaving a potential well. In clusters, a small gravitational redshift of galaxy light can be measured statistically, offering another probe of the potential and of gravity. Again, the misreading is to imagine dramatic differences in time flow across the cosmic web. The differences are tiny for typical structures, but they are part of the same geometric framework. In this region, the universe is still described as expanding still close to homogeneous at the widest scales, yet richly structured. Galaxy clusters, filaments, and voids are not merely features within a fixed space. They are the grown outcome of early variations, and they curve space-time in ways that can be observed through lensing, clustering distortions, radiation imprints, and the evolving abundance of massive systems. Reading this correctly requires keeping both levels in mind at once: the smooth background geometry that sets the overall expansion and the superposed evolving curvature of large structures that shapes the actual paths of light and matter across the cosmic web. The scale narrows from the cosmic web to the environment of a single galaxy, where space-time is still weakly curved compared with the extreme curvature near compact objects, yet the curvature is strong enough to govern the long-term motion of stars, gas, and satellite galaxies. A galaxy is not a solid body moving through empty space. It is a gravitationally bound system in which the dominant large-scale influence is the collective mass distribution, most of it in a dark matter halo that extends far beyond the visible starlight. In this region, it becomes easier to see how space-time is often misread, because everyday intuition expects gravity to act as a force pulling inward through a fixed stage, while the relativistic picture treats gravity as geometry shaping the natural paths of motion. For most galactic dynamics, the curvature is weak enough that the Newtonian limit of general relativity works extremely well, and astronomers commonly use the language of gravitational potential forces and orbital speeds. Yet even in this familiar language, the underlying misreading can be corrected by remembering that the potential is a convenient approximation to the metric in a slow-motion weak-field regime. In a spiral galaxy, stars orbit in a flattened disk. Gas also orbits and can cool collapse and form new stars in the spiral arms where density waves compress the material. In a simple picture where most mass is concentrated in the luminous disk, and bulge orbital speeds would decline with distance from the center, similar to planets in the solar system. Observations show that in many galaxies the rotation curves remain flat far beyond the bright stellar disk, meaning orbital speeds do not drop as expected. This is one of the key lines of evidence for extended dark matter halos. In geometric terms, the space-time curvature implied by the motions of stars and gas indicates more mass than what is seen in light. This is not a small correction. It dominates the mass budget on galactic scales. The misreading to avoid is that dark matter is introduced merely to save a theory. The claim is that multiple independent observations, including rotation curves, gravitational lensing, and the dynamics of satellite galaxies, point to a similar conclusion about unseen mass. Another misreading is to imagine dark matter as a kind of thick fog that drags on objects or blocks light. In the standard view, dark matter interacts very weakly with ordinary matter, and with light mainly through gravity. It forms extended halos because it can collapse gravitationally without radiating energy away, leaving it in a diffuse, roughly spherical distribution rather than a thin disk. Within a galaxy, the curvature of space-time determines how objects move when no other forces dominate. Stars follow nearly geodesic paths, though. They also respond to collective effects such as spiral density waves and to encounters with molecular clouds. Gas, unlike stars, can collide, shock and radiate, so its motion is not purely geodesic. Still, the overall shape of the galaxy and the broad patterns of motion reflect the gravitational field. The gravitational field is not static over cosmic time. Galaxies grow through accretion of gas, through mergers with smaller galaxies, and through the slow inflow of satellites along filaments. Each merger changes the mass distribution and in principle changes the metric in that region. The changes are gradual compared with the orbital times of many stars, but not always. In a major merger, the gravitational potential varies rapidly, and stellar orbits can be strongly rearranged, turning ordered disks into more random ellipsoidal systems. At this scale, the expansion of the universe is usually negligible for internal galactic dynamics because the galaxy is gravitationally bound. A common confusion is to ask whether expansion stretches a galaxy. In practice, the system is held together by gravity and other forces, and it does not participate in the Hubble flow in the same way as widely separated galaxies do. The appropriate description is that the galaxy is decoupled from the smooth expansion background, even though it exists within the larger expanding universe. The boundary between bound and unbound is not a hard shell, but a gradual transition in which the gravitational influence of the halo competes with the overall expansion and with the tidal fields from nearby structures. Around a galaxy there are satellite galaxies, globular clusters, and streams of stars that have been tidally stripped from smaller companions. These streams trace the gravitational potential over large radii. By mapping their positions and velocities, astronomers infer the shape and mass of the dark halo. The halo is not always perfectly spherical. Simulations suggest it can be somewhat triaxial, and it can be perturbed by mergers. Observations place constraints, though uncertainties remain due to limited data and to the complexity of modelling. Here, the principle of scientific accuracy requires care. The existence of a massive halo is strongly supported, but its detailed inner profile, its exact shape, and the distribution of substructure are still active topics. Subhalos. Smaller clumps of dark matter within the main halo are expected in cold dark matter models. Some are associated with visible dwarf galaxies, others may be dark. The number and distribution of these subhalos are tested through counts of satellite galaxies and through subtle lensing effects that can reveal small-scale mass clumps. These tests probe how matter behaves on scales far smaller than the cosmic web, but still much larger than any star system. Misreadings arise when the absence of an expected signal is taken as a decisive refutation, or when a single detection is treated as definitive confirmation. The current state is that many lines of evidence broadly support the cold dark matter framework, yet there are tensions on small scales that may reflect baryonic physics, observational limitations, or the need for refined dark matter properties. Within galaxies, space-time is also read through light propagation. Gravitational lensing by a galaxy can magnify and distort images of more distant objects. In strong lens systems, a foreground galaxy produces multiple images or arcs of a background quasar or galaxy. The detailed arrangement of images encodes the projected mass distribution of the lens galaxy, including its dark halo. This provides a way to measure mass without relying on the motions of stars and thus offers an independent check. In addition, light climbing out of the galaxy's gravitational potential is slightly redshifted. For a single star, this gravitational redshift is tiny compared with the Doppler shifts from stellar motion, but in large samples it can be measured statistically, especially in dense environments. Another route is to consider the central regions of galaxies where the curvature becomes stronger because mass is concentrated. Many galaxies host a supermassive black hole at their center, with a mass ranging from millions to billions of times the mass of the Sun. The evidence includes the rapid motions of stars and gas near the center, and in some cases direct imaging of the shadow region at radio wavelengths. Yet the present section stays at the scale of the galaxy as a whole, so the central black hole is noted only as part of the mass distribution that influences inner orbits. The deeper exploration of extreme curvature belongs to later sections. Still, even here, the presence of a central massive object illustrates a key point about misreading. It is tempting to picture a black hole as a dense object sitting in space and pulling on everything like a vacuum cleaner. The more accurate view is that outside the event horizon, the gravitational influence of the black hole is similar to that of any mass of the same size. And at the scale of the galaxy, the black hole's contribution to the total mass is usually small compared with the halo. It matters greatly for the dynamics of the inner parsec, not for the rotation curve at tens of kiloparsecs. The galaxy also contains magnetic fields, cosmic rays, and turbulent gas, and these non-gravitational components influence how matter moves and how stars form. They do not typically change the metric in a direct way, because their energy densities are small compared with the mass energy of the halo, but they shape the visible structure that observers use to infer the gravitational field. Feedback from supernovae and from active galactic nuclei can drive winds that expel gas and alter the distribution of baryonic matter. This can in turn modify the inner gravitational potential and potentially change the inferred dark matter profile in the central regions. This is another place where misreading can occur. The gravitational field inferred from visible matter is not fixed, and the interplay of baryons and dark matter is dynamic. Yet the broad conclusion remains that the galactic spacetime is largely set by the dark halo, with the luminous disk and bulge adding important structure, and with evolution through mergers and feedback shaping the details. In this region, spacetime is best read as a gently curved setting whose curvature is mapped by the orbits of stars and gas, and by the bending of light. The misreadings that fade are the idea that expansion directly stretches bound systems, and the idea that gravity is always a simple pull from visible matter alone. What becomes clearer is that even a single galaxy is a complex gravitational laboratory where the geometry implied by motion and lensing reveals a dominant unseen mass component, and where the distinction between the smooth cosmic background and the locally bound structure is essential for reading the fabric without importing everyday images that do not apply. The scale narrows again to stellar neighborhoods where the dominant gravitational sources are individual stars and the local distribution of gas and small bodies. Space-time here is still weakly curved in the sense that the gravitational potential is small compared with the square of the speed of light, yet it is strong enough to control the architecture of bound systems and the long-term evolution of orbits. A stellar neighborhood could mean the region within a few parsecs around a star, or it can mean the local environment within a galaxy, where many stars share similar motions and where interstellar gas and magnetic fields shape star formation. In either meaning, the region is closer to everyday scales, which makes misreadings more tempting because familiar images from classical mechanics feel applicable. The correction is not to discard those images entirely, since the Newtonian approximation often works well, but to keep track of where the approximation hides the deeper geometric structure and where it can fail. Around a typical star motion is governed mainly by gravity, which in general relativity is expressed by the curvature of spacetime. In the weak field slow motion limit, the metric can be written as a small deviation from flat spacetime, and that deviation is related to the Newtonian potential. The practical result is that planets, asteroids, comets, and dust grains follow trajectories that are close to ellipses, perturbed by the presence of other bodies and by non-gravitational forces such as radiation pressure and gas drag. The misreading to avoid is to treat these trajectories as happening in an absolute Euclidean space, with an independent time that is the same everywhere. Even in a stellar neighborhood, clocks at different gravitational potentials tick at slightly different rates, and moving clocks tick differently from stationary ones when compared. These effects are tiny in many contexts, but they are measurable, and they matter for precision navigation, for the timing of pulsars, and for interpreting high-accuracy astronomical data. A useful example of a local stellar laboratory is a binary system where two stars orbit their common center of mass. The gravitational interaction is strong enough that relativistic corrections can become significant, especially if one or both stars are compact objects. For ordinary main sequence stars separated by large distances, Newtonian gravity describes the orbit well. For tight binaries containing white dwarfs, neutron stars, or black holes, the curvature is stronger and velocities are higher, and the orbit shows relativistic features. One such feature is the gradual precession of the orbit's closest approach point, analogous to the perihelion advance in planetary motion, but often much larger in compact binaries. Another is gravitational time dilation, which affects the rates of clocks tied to different parts of the orbit. In the most compact systems, energy is carried away by gravitational waves, causing the orbit to shrink over time. This energy loss has been measured indirectly through the changing orbital period of binary pulsars, and directly through gravitational wave detections from merging compact objects. The misreading here is to picture gravitational waves as sound waves travelling through a material ether. They are changes in the metric that propagate at the speed of light carrying energy and angular momentum. Their effect on a stellar neighbourhood is minuscule unless the source is extremely strong or extremely close, but their existence confirms that space-time geometry is dynamic. A different kind of stellar neighbourhood laboratory comes from pulsars. A pulsar is a rapidly rotating neutron star that emits beams of radio waves. As the star spins, the beam sweeps past Earth like a lighthouse producing pulses that can be timed with extraordinary precision. Pulsar timing allows tests of relativity because the pulses act as a stable clock. In a binary pulsar, the timing reveals not only the Keplerian orbit, but also relativistic corrections, gravitational redshift and time dilation near periastron, the Shapiro delay, where pulses passing near a companion take extra time due to curved spacetime, and the orbital decay from gravitational radiation. In a cluster of stars or in a region of dense interstellar medium pulsars can also probe the gravitational potential and the distribution of matter. This is still within a stellar neighbourhood because the distances involved are small compared with galactic scales, yet the precision is enough to make space-time effects visible. Closer to the everyday, the neighbourhood around a star is filled with plasma magnetic fields and radiation. These influence matter through forces that are not geometric in the same direct way as gravity, but they operate within the same space-time. Stellar winds stream outward from many stars carrying charged particles that interact with planetary magnetospheres and shape astrospheres, the bubble-like regions carved in the interstellar medium. The structure of an astrosphere is often described in fluid terms with shock, fronts, and pressure balance. The misreading here is to assume that because plasma dynamics dominates space-time is irrelevant. Gravity still sets the overall gravitational well, determines escape speeds, and influences how gas and dust are retained or lost. The interplay of radiation and gravity is also important for small particles. Dust grains feel radiation pressure from starlight, and the ratio of radiation pressure to gravity depends on grain size and composition. In addition, the Poynting-Robertson effect causes dust to lose angular momentum and spiral inward slower because of the way absorbed and re-emitted radiation carries momentum in the grain's frame. These processes are described well in classical terms, but they fit into the relativistic framework where energy and momentum exchange is consistent with the geometry. Another common misreading concerns what is meant by a local inertial frame. In relativity over a sufficiently small region of space and time, it is possible to choose coordinates in which the laws of physics look like those of special relativity with space-time nearly flat. This leads to the idea that gravity can be transformed away locally. The important limitation is that this is true only at a point or over a region small enough that tidal effects are negligible. Tidal effects reflect the fact that curvature varies across space. In a stellar neighbourhood, tides are evident in the way a star's gravity stretches an extended body. They raise tides on planets can disrupt comets and can tear apart a star that passes too close to a black hole. Even far from black holes, tides in a star-planet system can dissipate energy and alter spin rates and orbital distances over long times. This is a direct, tangible expression of curvature gradients, and it is a reminder that gravity is not merely an acceleration that can be removed by adopting a freely falling frame everywhere. The neighbourhood within a galaxy also includes the gravitational influence of nearby stars. In the solar neighbourhood of the Milky Way, stars move in a common galactic potential, but also experience encounters. Most encounters are distant and weak, producing small changes in velocity. Over billions of years, these encounters contribute to the gradual heating of stellar motions, increasing random velocities and thickening the disk. In dense environments like globular clusters, close encounters are more frequent, leading to exchanges in binary systems, ejections of stars, and the formation of exotic objects. These are dynamical effects in a many-body gravitational system. General relativity is not usually required for the bulk behavior, but it becomes important for compact remnants and for high-precision timing signals. Misreadings often come from treating a stellar neighborhood as if it were isolated. In reality, the neighborhood is embedded in the galactic potential and is subject to tidal fields from the larger mass distribution. The concept of a tidal radius defines a boundary beyond which a star cluster's members are more strongly influenced by the galaxy than by the cluster itself. This shows again the hierarchy of scales local spacetime curvature from a star is superposed on a broader curvature from the galaxy. Within this region, time is also read through gravitational and kinematic effects that become measurable in modern systems. For example, precise atomic clocks and satellite navigation must account for both special relativistic time dilation due to satellite speed and general relativistic gravitational time dilation due to altitude differences. Though these are Earth-based examples, they are expressions of the same principles that apply around any star and any planet. In astrophysics, similar corrections appear in interpreting signals from fast-moving stars near massive objects and in the timing of pulsars. At the scale of stellar neighborhoods, space-time is misread when it is treated as perfectly flat and universal, when gravity is treated as only a force with no relation to time, or when local systems are treated as completely detached from larger curvature fields. Reading it correctly means recognizing that classical orbits are accurate approximations to geodesic motion in weak curvature, that time flow is subtly environment dependent, that tides reveal curvature gradients, and that precision phenomena in binaries and pulsars make the geometry of space-time visible, even far from the dramatic regimes of event horizons. A planetary system is a bound arrangement of bodies orbiting a star, and it sits one step inward from the broader stellar neighborhood because its defining feature is a shared central gravitational source and a relatively tight range of distances and timescales. The geometry of space-time in such a system is usually weakly curved, yet it is read with unusual clarity because the motion of planets is orderly enough to reveal small departures from simple predictions. A persistent misreading begins with the assumption that an orbit is a path drawn in a fixed three-dimensional space, while time flows uniformly for all parts of the system. In the Newtonian picture, gravity is a force acting instantaneously at a distance, and time is an external parameter. In the relativistic picture, the star and the orbiting bodies shape a space-time in which the natural free-fall paths are geodesics, and in which the rate at which time passes is linked to gravitational potential and motion. For most planetary systems, Newtonian gravity provides an excellent approximation, but the relativistic reading becomes necessary when observations reach high precision, or when bodies approach very close to the star. The simplest planetary orbit is an ellipse, with the star near one focus, but real systems are rarely simple. Multiple planets interact, producing slow changes in orbital shapes and orientations. These interactions are described by perturbation theory and by numerical integration. In geometric terms, the paths are not isolated geodesics in a fixed metric. They are motions within a space-time influenced by the distribution of mass and energy in the system, including the star planets, moons, and even extended structures like disks of gas and dust. Yet because the star dominates the mass, the leading description treats the star's gravitational field as the primary curvature, and treats the planets as test bodies whose influence is small. This approximation becomes less accurate in systems with massive planets close to the star, or in systems with planets of comparable mass, but it remains a useful starting point. One of the clearest relativistic signatures in a planetary system is the advance of the orbit's closest approach point over time, a slow rotation of the ellipse within its orbital plane. In the solar system, Mercury shows a small extra precession beyond what Newtonian perturbations from other planets predict, and general relativity accounts for that extra amount through the curvature associated with the Sun. The effect is tiny, but it is a direct example of how space-time is read through planetary motion. The misreading to avoid is that relativity replaces the Newtonian account entirely in such cases. The correct view is that the Newtonian description captures most of the behavior and relativity supplies a small correction that becomes visible in precise measurements. A similar correction appears in the timing and frequency of signals exchanged between bodies. Light or radio waves climbing out of a gravitational potential are redshifted, and clocks deeper in a potential well tick more slowly when compared with clocks farther out once the comparison is made through signal exchange and proper accounting. In a planetary system, these effects can matter for navigation and for interpreting radio science experiments. They also matter for the stability of timekeeping when atomic clocks are carried on spacecraft. The point is not that time behaves dramatically differently from one planet to another in ordinary circumstances. The differences are small, but they are real, and they are part of the same geometric structure that governs orbital motion. Another misreading concerns what is meant by the plane of an orbit and the constancy of that plane. In Newtonian gravity with a spherical central mass, the orbit lies in a fixed plane because angular momentum is conserved. In a real system, the star can rotate, its mass distribution can be slightly flattened, and its gravitational field can deviate from perfect spherical symmetry. This produces additional precession of orbital planes and of the line of nodes. In strong field situations, a rotating compact object can drag inertial frames around it, an effect known as frame dragging. But in planetary systems around ordinary stars, the analogous relativistic contribution is extremely small compared with classical effects from ablateness and from planetary interactions. Misreading arises when frame dragging is imagined as a large whirlpool in space that twists everything nearby. In practice, for stars like the Sun, the effect on planetary orbits is far below the dominant perturbations. It is a subtle correction more relevant in the vicinity of rapidly rotating compact objects than in typical planetary systems. Planetary systems also contain smaller bodies and extended material that reveal the system's formation and evolution. Protoplanetary disks are rotating disks of gas and dust around young stars from which planets form. The disk's gravity can influence migrating planets and can shift orbital resonances. Gas drag and disk torques can move planets inward or outward over time, changing their final arrangement. These processes belong to the dynamics of matter and forces within space-time, rather than to geometry alone, yet the geometry sets the baseline for orbital energies and angular momenta. The misreading to avoid is to treat the architecture of a system as a static outcome. Many systems undergo migration scattering and resonant capture. Resonances occur when orbital periods fall into simple ratios, allowing repeated gravitational tugs that can stabilize or destabilize configurations. In resonant chains, small changes can propagate through the system, and the long-term stability depends on subtle balances. These are best described with dynamical systems language, but the underlying point remains that the orbits are paths in a curved space-time, where the star's mass sets the main curvature and the planets perturb one another. The detection methods used in modern astronomy also highlight how space-time is read in planetary systems beyond the solar system. When a planet passes in front of its star along the line of sight, the star's brightness dips slightly in a transit. The timing and depth of these dips reveal the planet's size relative to the star and the orbital period. When a planet tugs on its star, the star moves in a small orbit around the system's center of mass, shifting its spectral lines through Doppler motion. The combination of transit and Doppler data can give a planet's density and hint at its composition. In addition, variations in transit timing can reveal gravitational interactions among planets, offering a way to measure masses and orbital eccentricities even when Doppler signals are small. These techniques rely on the predictable propagation of light and on the precise timing of periodic events. If the geometry were misread as a rigid stage, the subtle timing effects that arise from gravitational time dilation or from light travel time across the system could be overlooked. In practice, high-precision analyses include these corrections when needed, and they become more important as measurement precision improves. Within planetary systems, an especially important inward step is the region where light and matter exchange energy, such as the atmospheres of planets and the surfaces of moons, but that belongs to later sections. For the present region, the focus stays on the orbital space-time around the star. Here, stability is a central theme. In a simple two-body system, a bound orbit can persist indefinitely in the absence of perturbations. In real systems, tides raised on planets and on the star dissipate energy, gradually changing rotations and orbital distances. A close-in planet can spiral inward over long times if tidal dissipation extracts orbital energy. A moon can drift outward if tidal torques transfer angular momentum from a planet's spin to the moon's orbit, as in the Earth-Moon system. These processes are not primarily relativistic, but they unfold within the space-time curvature set by the masses involved, and they show that planetary systems evolve even when no external encounters occur. A misreading arises when tides are treated as purely oceanic phenomena. Tides are a gravitational effect on extended bodies, and they act on solid rock and on gas as well as on water. They also reveal curvature gradients in a practical way because they depend on how gravity changes across an object's size. Another subtle inward link concerns the distribution of mass within the star itself. For most orbital dynamics, the star can be treated as a point mass, but precision can require knowledge of its quadrupole moment set by the rotation and internal structure. This influences the precession of close orbits. In some cases, the star's activity mass loss or magnetic braking changes its rotation rate over time, altering these effects. Again, the misreading to avoid is to imagine a perfectly unchanging central mass. Real stars evolve and interact with their systems. Even small changes can matter for close-in planets over long periods. At the scale of planetary systems, space-time is therefore read through stable periodic motion, tiny precessions, and precise timing, all of which sit comfortably in the weak field regime while still reflecting the deeper geometry. The fabric is misread when orbital motion is imagined as purely force-driven in an absolute space with universal time, when relativistic corrections are treated as dramatic rather than subtle, or when the long-term evolution driven by tides and interactions is neglected. Read carefully. The planetary system becomes a quiet laboratory where the geometry around a star is mapped by the regularity of orbital paths and by the small measurable departures that accumulate over many revolutions. The scale narrows to planetary surfaces and the thin layers above and below them, where spacetime is experienced through the combined effects of a planet's gravity, rotation, shape, and environment. This region is close enough to everyday life that misreadings become especially persistent because the sensations of weight, the rhythm of days and nights, and the apparent constancy of time encourage the idea that gravity is simply a downward pull and that time is the same everywhere on a planet. The corrected reading keeps the calm fact that even at a planetary surface, the geometry of space-time shapes measurable differences in time flow and in the paths of moving objects while remaining firmly in the weak field regime where classical intuition works well most of the time. A planet is not a perfect sphere. Rotation causes it to bulge slightly at the equator, making the equatorial radius larger than the polar radius. The surface is also not smooth. Mountains, ocean trenches, and variations in crustal density create small differences in gravitational potential. These variations influence the direction a plumbline points and the level surfaces that define sea level and altitude. The idea of a level surface is already geometric. It is an equipotential surface on which a test mass would have the same gravitational potential energy per unit mass, including the effects of rotation. On Earth, the geoid is an irregular equipotential surface that approximates mean sea level. This is often misread as an arbitrary reference rather than as a physical manifestation of the planet's gravitational field. The gravitational field at a surface can be described as an acceleration, but in general relativity it also corresponds to how the metric differs from flat spacetime. A clock on the surface ticks slightly more slowly than a clock far away from the planet when compared by exchanging signals and accounting for motion. The difference is small, but it is real, and it matters in modern timekeeping. In practical systems like satellite navigation, both special relativistic time dilation from satellite speed and general relativistic gravitational time dilation from satellite altitude must be corrected for, or position errors would grow quickly. This is a strong antidote to the misreading that relativity is only for exotic astrophysics. On a planet, the rate of time also varies with altitude. A clock higher up, deeper in less negative gravitational potential ticks slightly faster than a clock at sea level, all else equal. Over a day, the difference is tiny, but modern optical clocks are precise enough to detect changes corresponding to height differences of less than a meter under controlled conditions. This shows that even the everyday notion of time is linked to geometry. Another common misreading is to treat gravitational acceleration as uniform. On Earth, acceleration varies with latitude because rotation reduces effective weight at the equator, and because the equatorial bulge increases distance from the center. It also varies with local geology. These variations are mapped by gravimetry and by satellite missions that track the planet's gravity field. The results are not just curiosities, they inform geophysics, oceanography, and climate science by revealing mass redistribution in ice sheets, groundwater, and ocean circulation. The link to space-time remains quiet but present. The gravitational potential is part of the metric, and changes in mass distribution correspond to small changes in that potential. The planetary surface is also where motion through the atmosphere and across terrain introduces speeds that are small compared with the speed of light, making special relativistic effects negligible in most daily activities. Yet rotation introduces a global motion. Points on the equator move faster than points near the poles relative to an inertial frame. This contributes a small kinematic time dilation, making clocks at the equator tick slightly more slowly than clocks at the poles when compared in the same gravitational potential. At the same time, the equatorial bulge means the equator is at higher altitude, and thus at higher gravitational potential, which makes clocks tick slightly faster. The net difference depends on the planet's parameters and the reference used. For Earth, these effects nearly cancel for sea-level clocks, leading to a subtle balance that is a practical example of how geometry and motion interplay. The misreading to avoid is that any of these differences is large enough to be felt directly. They are not. They become visible through careful measurement. The surface is also the stage for trajectories of projectiles, aircraft, and satellites in low orbit. In classical physics, a projectile follows a parabola in a uniform gravitational field, and an orbiting satellite follows an ellipse around the planet's center. In general relativity, both are approximations to geodesic motion in a curved spacetime. The difference between a satellite and a projectile is mainly one of speed and altitude. The satellite's forward speed is high enough that it continuously falls around the planet. The misreading to avoid is to imagine orbit as weightlessness because gravity disappears. In orbit, gravity is still strong. Weightlessness arises because the satellite and its contents are in free fall together, following a geodesic, so there is no support force. This is an inward bridge from planetary surfaces to the broader idea that gravity is not simply a force, but can be understood as the geometry that free-falling bodies follow. The atmosphere introduces additional forces that break free fall. Drag removes energy and causes low satellites to spiral inward, and it shapes the paths of meteoroids and spacecraft. Atmospheric density varies with altitude, time of day, and solar activity, so drag is not constant. The misreading to avoid is to treat the atmosphere as a fixed shell. It is dynamic and coupled to the planet's rotation, heating, and magnetic environment. Yet gravity still sets the vertical stratification with pressure and density generally decreasing with height, because the weight of the overlying air must be supported. The scale height, the characteristic height over which pressure falls by a factor of about 2 and a bit, depends on temperature and molecular mass. This is everyday physics, but it is also tied to the planetary gravitational potential. The surface environment also includes the planet's magnetic field and its interaction with solar or stellar wind, creating magnetospheres, auroras, and radiation belts. These phenomena are not primarily about space-time curvature, but they occur within it, and they influence how signals propagate. Radio waves passing through the ionosphere can be delayed and refracted, affecting navigation and communication. Precision timing and positioning therefore require models of atmospheric and ionospheric effects, in addition to relativistic corrections. Misreading can occur when a timing error is attributed to relativity or to gravity alone, ignoring the layered contributions of the medium. The surface is also where the planet's interior makes itself known. Variations in gravity reflect differences in crustal thickness and mantle density, and seismic waves reveal the layered structure of the interior. The interior belongs to a later inward step, but the surface is where those deeper layers are measured. In this region, one more misreading concerns what it means to stand still. On a rotating planet, standing still on the surface means moving in a circle in an inertial frame. This introduces Coriolis and centrifugal effects in the rotating frame that influence winds, ocean currents, and the trajectories of long-range projectiles. These are not relativistic effects. They are consequences of using a non-inertial frame. Yet they echo a deeper point. The choice of reference frame matters for how motion is described, and apparent forces can arise from that choice. In relativity, coordinate choices also matter, and the cleanest physical statements are those expressed in invariant quantities like proper time along a world line. On a planetary surface, proper time is what a clock measures locally, and different world lines through space-time can accumulate slightly different amounts of proper time between the same endpoints. This becomes tangible in experiments where clocks are flown on aircraft or placed at different altitudes and then compared. The differences match relativistic predictions within experimental uncertainties, reinforcing the geometric reading even in familiar environments. At the scale of planetary surfaces, then space-time is read in quiet gradients. Gravity varies with latitude and geology. Time flows at slightly different rates with altitude and motion. Free fall reveals weightlessness without removing gravity. Rotation shapes trajectories and produces apparent forces in the rotating frame. The fabric is misread when gravity is treated as uniform and purely downward, when orbit is treated as beyond gravity when time is assumed to be identical everywhere, or when the effects of media like the atmosphere are ignored in precision measurements. Read carefully. The planetary surface becomes a place where the geometry of space-time is present not as drama, but as a steady set of measurable relations linking mass distribution motion and the ticking of clocks. Everyday gravity is the inward step where space-time is encountered most directly through the simple fact of weight and the steady fall of objects, yet it is also the step where misreadings are most entrenched, because daily experience encourages a particular story. The familiar story says that gravity is a force pulling objects downward toward the center of a planet acting in a fixed space while time flows uniformly in the background. This story predicts much of what is observed, and it remains a very effective approximation in ordinary conditions. The misreading is not that the story is useless. The misreading is that it is complete. In the relativistic reading, what is called gravity in daily life is the combination of space-time curvature and the fact that standing on a surface is not free fall. The sensation of weight is not the feeling of gravity pulling downward. It is the feeling of a support force pushing upward to keep a body from following its natural freefall path. This difference is subtle in language but clear in physics. A person standing on the ground is being prevented from moving along a geodesic, and the deviation from geodesic motion is what produces proper acceleration. The acceleration an accelerometer would measure. The same accelerometer would read nearly zero in freefall even though gravity is present. This is why astronauts in orbit feel weightless, and why an elevator cable snapping produces a momentary feeling of weightlessness. The body is not relieved of gravity, it is relieved of the support force. The everyday case of dropping an object illustrates the same point. Released from rest relative to the surface, the object begins to follow a freefall trajectory. In Newtonian terms, it accelerates downward because of gravitational force. In relativistic terms, it moves along a geodesic in curved space-time, while the surface beneath is a non-inertial reference frame supported by electromagnetic forces in the material. The ground is not following a geodesic. It is continually accelerating upward in the local freefall frame, and this is what a scale measures as weight. This reframing often feels like wordplay, but it has practical content. It explains why in a small, freely falling laboratory, the laws of physics look almost like those of special relativity, with objects floating and drifting as if gravity is absent, even though the laboratory is inside a gravitational field. This is the equivalence principle in its simplest form. The misreading to avoid is that the equivalence principle means gravity is unreal. Gravity is real as curvature, and curvature shows itself through tidal effects, the variations of freefall acceleration across space. Tidal effects are the signature that cannot be eliminated by choosing a freely falling frame over an extended region. Even near Earth's surface, tides are measurable. They raise ocean tides, but they also stretch the solid Earth and influence precise gravimetry. They exist because the gravitational field is slightly stronger closer to the planet's center and slightly weaker farther away. Two objects dropped side by side remain nearly parallel, but two objects dropped from different heights converge slightly because their freefall paths are not exactly parallel in a curved geometry. In daily life, the differences are too small to notice, but they are the same type of effect that becomes dramatic near compact objects. Another misreading is to imagine that curvature must be visualized as a rubber sheet dented by a heavy ball. This picture can help convey that mass affects geometry and that trajectories bend, but it smuggles in an external downward direction and a surrounding space. In everyday gravity, the most reliable way to keep the geometric meaning is to focus on measurable consequences, how clocks tick, how rulers measure distance, and how free-falling trajectories behave. Even on Earth, time is affected by gravity. Clocks at higher altitude tick faster than clocks at lower altitude by a tiny amount. This has been demonstrated by comparing atomic clocks at different heights and by transporting clocks and bringing them back together. The difference is not a philosophical claim. It is a measured accumulation of proper time along different world lines. The misreading is to treat this as an exotic effect that only matters in space travel. In practice, modern navigation and timing systems incorporate it. In addition to gravitational time dilation, special relativistic time dilation due to motion also plays a role in systems involving aircraft and satellites. These effects can be described as separate contributions in weak fields, but they are unified in the space-time interval that determines proper time. Everyday gravity also includes the fact that the gravitational field is not constant in time. Mass moves. The Moon and Sun produce tides that change the local gravitational acceleration slightly over hours. Groundwater shifts atmospheric pressure changes, and ocean mass redistribution alter the gravitational field at the microgal level, and sensitive instruments measure these variations. Earth itself is not rigid. It deforms under tidal forces and under the changing load of water and ice. This reveals another misreading, the idea that gravity is a fixed property of a location independent of what is happening. Gravity is linked to mass energy distribution, and that distribution evolves. In most daily contexts, the changes are too small to matter, but they are part of the correct reading fabric. In everyday motion, the influence of gravity is often combined with the effects of rotation and non-inertial frames. On Earth, the apparent downward direction is defined by the net of gravitational and centrifugal effects. This is why a plumb line does not point exactly toward Earth's center. The centrifugal contribution reduces effective weight slightly more at the equator than at the poles. In a rotating frame, apparent forces such as Coriolis appear influencing winds and ocean currents. These are not relativistic, but they demonstrate that descriptions of motion depend on the chosen frame. A misreading occurs when apparent forces are treated as if they are mysterious new interactions rather than artifacts of a rotating coordinate system. Relativity extends this lesson. Coordinate descriptions can introduce effects that are not fundamental, and the invariant quantities are those that all observers can agree on, such as the proper time along a path and the curvature measured by tidal effects. Everyday gravity is also where the speed of light enters as a practical limit. Signals propagate at a finite speed, so a change in mass distribution affects distant gravitational measurements with a delay. In daily life, this delay is negligible for most purposes, and Newtonian gravity treats the field as adjusting instantaneously. General relativity replaces this with a field that can propagate changes at the speed of light consistent with causality. The misreading is to insist that because Newtonian gravity works locally, instantaneous action must be literally true. In reality, the difference matters in systems with rapidly changing mass distributions, or in the propagation of gravitational waves. The everyday environment does not usually reveal this, but it is part of the consistent framework. Another everyday arena for reading space-time is acceleration. In a rocket accelerating in deep space far from masses, a person feels a force similar to weight. Objects released inside the rocket fall toward the floor. A clock at the nose of the rocket ticks at a slightly different rate than a clock at the tail when compared through light signals because of the relativity of simultaneity and the way acceleration affects time slices. In a small region, this situation is locally equivalent to a uniform gravitational field. This is another way to understand that weight is linked to being held away from freefall, whether by a planet's surface or by an accelerating vehicle. The misreading to avoid is to treat gravity as something that can always be distinguished immediately from acceleration. Locally, they can be equivalent in their effects, and distinguishing them requires looking for tidal signatures or for the global structure of the field. In daily life, measurement itself imposes limits. A person can sense weight changes caused by an elevator accelerating or by standing on a scale in a moving vehicle, but cannot sense the tiny changes from gravitational time dilation. Yet instruments can. This difference between sensory intuition and instrumented reality is one reason space-time is so often misread. The human body evolved to operate in a narrow range of speeds and gravitational potentials where Newtonian approximations are excellent. The deeper geometry becomes visible only when measurements become precise or when conditions become extreme. Everyday gravity sits exactly at the boundary where both descriptions meet. The familiar force picture remains practical, while the geometric picture explains why freefall is inertial motion and why time itself depends on gravity and motion. In this region, the fabric is misread when weight is taken as direct evidence of a downward gravitational pull acting on a stationary body when freefall is treated as a state of being pulled rather than released, when curvature is imagined only as a visual dent in an external space, and when time is treated as universal and unaffected by position and motion. Read carefully. Everyday gravity becomes a steady lesson. The ground is what accelerates free fall, is what reveals inertial motion in curved space-time tides, are what reveal curvature gradients, and clocks, not sensations, reveal how gravity and motion quietly shape the passage of time. Time dilation is one of the most measured and yet most misread features of space-time, because it collides with the deeply held expectation that time is the same everywhere and for everyone. In the relativistic reading, time is not a universal river. Each physical clock measures its own proper time along its path through space-time, and different paths can accumulate different amounts of proper time between the same two events. This is not presented as a matter of perception or belief. It is a matter of what clocks record and what signal comparisons reveal. Time dilation appears in two intertwined forms: kinematic time dilation associated with relative motion in special relativity, and gravitational time dilation associated with differences in gravitational potential in general relativity. In the weak field conditions of most of the universe outside compact objects, these can be treated as separable contributions to good approximation, though the deeper structure is unified in the space-time interval and the metric. A central misreading is to treat time dilation as an optical illusion caused by slow signals, as if a moving clock only appears slow because light from it takes longer to arrive. Signal delay is a real observational issue, but time dilation remains after correcting for it. In laboratory tests, clocks are compared by bringing them together after different journeys or by exchanging signals with known delays removed, and the differences remain. Another misreading is to treat time dilation as symmetrical in all situations, and therefore as a paradox with no resolution. In special relativity, uniform relative motion is symmetric in the sense that each inertial observer can describe the other's clock as running slow while they remain separated. The symmetry is resolved when a comparison is actually made, because making a comparison requires bringing clocks together or exchanging signals within a defined procedure, and those procedures involve paths through space-time that need not be symmetric. The simplest example is the twin scenario, in which one clock follows a path that includes acceleration to turn around and return, while the other remains in one inertial frame. The difference in proper time is then not a matter of viewpoint. It is a geometric difference in the lengths of world lines in space-time, where length is measured in time units. In this inward region, time dilation becomes a tool. It is used to test relativity and to operate technology. Kinematic time dilation is measured in particle physics, where unstable particles created at high speed live longer in the laboratory frame than they do at rest, consistent with the prediction that moving clocks run slow. The particles are not believed to decide to decay later. Their internal processes, which act as a kind of clock, progress in proper time, and the relationship between proper time and coordinate time changes with velocity. The same effect is measured in storage rings and in beams of muons produced in the atmosphere, where many more reach the ground than would be expected without relativistic time dilation. These are not niche curiosities. They are routine confirmations that the time part of space-time depends on motion. Yet the misreading persists because everyday speeds are far too low for the effect to be noticed without precision clocks. Gravitational time dilation is measured by comparing clocks at different heights or in different gravitational environments. In a static gravitational field, a clock deeper in this potential well ticks more slowly relative to a clock higher up when compared by exchanging signals and correcting for motion. This is sometimes misread as a claim that time itself physically thickens near a mass, as though time were a substance. The more accurate statement is that the metric component that links coordinate time to proper time varies with gravitational potential, and this variation is read through frequency shifts in signals and through accumulated differences in clock readings. A related misreading treats gravitational redshift as separate from time dilation, as though light somehow loses energy while climbing out of gravity without any connection to clocks. The frequency of light is measured by comparing it to a clock. When a photon emitted from lower potential is received at higher potential, the received frequency is lower when measured against the receiver's clock. In the standard explanation, this can be seen either as a photon energy change in a gravitational field or as a difference in clock rates between emitter and receiver. Both descriptions are consistent within general relativity, and the invariant statement is about the relationship between emitted and received frequencies along a null path in the given metric. Time dilation also appears in global systems like satellite navigation. Satellites move fast enough for kinematic time dilation to slow their onboard clocks relative to the ground clocks, while their higher altitude places them in a weaker gravitational field, making their clocks tick faster relative to ground clocks. The combined effect is substantial enough that without correction, positioning errors would accumulate rapidly. This is an everyday operational fact that undermines the misreading that relativistic time is only relevant to black holes or to philosophical debate. The corrections are calculated using the known gravitational potential of Earth, including its shape and rotation, and using the satellite's orbits and speeds. Small additional effects, such as those due to Earth's quadrupole moment and to signal propagation through the ionosphere and troposphere, are also modelled. The resulting system works because the relativistic framework connects geometry, motion and timekeeping in a consistent way. Another subtle misreading is that time dilation implies that an observer can somehow watch their own time slow. In proper time, each clock always ticks normally according to itself. Time dilation is revealed only by comparing different clocks after different motions or in different potentials. A clock does not feel its own slowing because it does not slow in its own frame. It is the relation between clocks that changes. This matters when interpreting experimental results. For example, when precise clocks are flown on aircraft and then compared with clocks that remain on the ground, the differences reflect both the aircraft's speed and its altitude, and the predictions require careful integration along the flight path, accounting for variations in speed, altitude, and gravitational potential. Such experiments match general relativity within uncertainties, reinforcing the view that proper time depends on the path through space-time, not on subjective impressions. Time dilation also shapes astrophysical observations. In strong gravitational fields, signals from orbiting matter can be gravitationally redshifted, and their time variations can be slowed as seen by distant observers. In the disks around compact objects, rapid motions and deep gravitational potentials combine to produce large shifts and distortions of spectral lines. In the current region, the focus remains on time dilation as a measurable effect that grows more significant as conditions approach stronger curvature or higher velocities without yet entering the deepest regimes of neutron stars and event horizons. Still, even outside extreme objects, time dilation appears in the timing of pulsars and in binary systems. In a binary pulsar, pulses arriving on Earth carry signatures of gravitational redshift and time dilation as the pulsar moves in an elliptical orbit. Near closest approach, the pulsar moves faster and is deeper in the companion's gravitational potential, altering the pulse timing in predictable ways. The Shapiro delay adds another effect. Pulses passing near the companion take extra time because space-time curvature lengthens the light path relative to a flat space estimate. These phenomena are sometimes misread as separate ad hoc corrections. In general relativity, they arise naturally from the metric and from the null geodesics that signals follow. The result is a self-consistent timing model that can be tested with high precision. A further misreading concerns simultaneity. Time dilation is often discussed as a simple slowing, but special relativity also changes what is meant by events being simultaneous. Observers in relative motion disagree about which distant events occur at the same time, and this disagreement is not a mistake. It reflects the geometry of Minkowski spacetime, where time and space coordinates mix under changes of inertial frame. This is not yet the main focus of the present section, but it is closely tied to how time dilation is understood correctly. Without appreciating the relativity of simultaneity, it is easy to imagine that there is a hidden universal time in the background, and that time dilation is merely a distortion of measurements. The consistent reading is that there is no single global slicing of spacetime into universal now surfaces, that all observers share even in flat spacetime, and that time dilation and simultaneity are part of one unified structure. At this level, it also becomes clear why time dilation is not a mere technicality but a central feature of the fabric. Space-time is the set of relations that connect events, and time is one dimension of those relations. If the geometry changes with motion, or with gravitational potential, then the amount of proper time between events depends on the path taken. This is as concrete as distance depending on the route on a curved surface, except that in space-time the metric signature makes time behave differently from space, allowing one path to maximize proper time between events while another yields less. This geometric perspective avoids the misreading that time dilation is a psychological effect, a trick of light, or a contradiction. It treats it as the natural outcome of how the universe measures intervals. The remaining uncertainties in this region are not about whether time dilation exists, because it is well confirmed, but about how it should be described in more complex situations, where gravity is not static, where space-time is not well approximated by simple metrics, or where quantum effects might affect timekeeping at very small scales. Those deeper questions belong further inward. For now, time dilation stands as a steady measured property of space-time that connects laboratory particles, precision clocks, satellites, and astrophysical systems under one calm rule. Different motions and different gravitational environments lead different clocks to accumulate different amounts of proper time. And the differences are not matters of appearance, but of what clocks record when they are compared through careful procedures. The relativity of simultaneity is the inward step where the fabric is most often misread, because it challenges the idea that there is a single shared present moment stretching across space. In everyday life, distances are small and speeds are low, so it feels safe to assume that two events happening far apart can be said to occur at the same time, in an absolute sense. Clocks can be set, schedules can be agreed upon, and the delays in signals are usually negligible. In the relativistic reading, simultaneity is not absolute. It depends on the state of motion of the observer and on the method used to synchronize clocks across space. This does not mean that anything can be made simultaneous by choice or that time is arbitrary. It means that the division of space-time into slices labeled as now is not unique when observers are in relative motion. The physical content remains in invariant relationships, such as whether one event can influence another, and in measurable quantities such as proper time along a path. The misreading to avoid is that relativity turns time into mere opinion. It does not. It changes which coordinate assignments are natural for different inertial frames, and which distant events are assigned the same coordinate time. The classic way to define simultaneity within an inertial frame uses light signals. A clock at one location sends a signal to a distant clock and receives a reflection. If the signal leaves at one time and returns at another, the distant event of reflection is assigned a time halfway between the send and receive times, assuming light travels at the same speed in both directions in that frame. This convention is consistent with the postulates of special relativity and with vast experimental evidence. It is not the only imaginable convention in a purely philosophical sense, but it is the one that makes the laws of physics take their simplest form in inertial frames, and matches how clocks and signals behave in practice. Once this is adopted, it follows that observers in relative motion who each use this procedure within their own inertial frames will disagree about which distant events are simultaneous. The disagreement is not due to signal delay, because signal delays are part of the synchronization procedure and are corrected for. The disagreement arises because space and time coordinates mix under Lorentz transformations, the mathematical relation between inertial frames in special relativity. A central misreading treats this as a problem that could be removed by finding the correct frame. In special relativity, no inertial frame is privileged by the laws of physics. Each inertial frame can define its own simultaneity slices consistently. Another misreading treats simultaneity as something that must be directly observed. In fact, simultaneity is a convention tied to how distant times are assigned and compared. What is directly observed are local events and signal arrivals. The structure of space-time tells how these observations are related across frames. The relativity of simultaneity becomes clearer when considering simple thought experiments with clocks and moving observers, but here it is described in the same calm, third-person way, without dialogue. Imagine two clocks at rest relative to each other, separated by a fixed distance synchronized in their rest frame by the light signal method. In their frame, the clocks show the same time at the same moment. Now consider an observer moving relative to these clocks. In the moving observer's inertial frame, the two clocks are not at rest, they move together. The moving observer can also define simultaneity using the same method within their frame. When the moving observer assigns times to events on the two clocks that are simultaneous in the moving frame, they find that the two clocks do not show the same reading at those events. One clock is ahead of the other by an amount proportional to their separation and to the relative speed divided by the square of the speed of light. The effect is small at everyday speeds, but it is a direct consequence of the geometry of Minkowski spacetime. The misreading is to interpret this as the clocks being broken, or as one observer making a mistake. Both sets of clock readings are correct locally. The difference lies in which pairs of distant events are labelled as simultaneous. This has practical consequences in systems that require high-precision timing across moving platforms where synchronization conventions must be chosen and implemented consistently. Simultaneity is also tied to time dilation in an important way. Time dilation is often described as one moving clock running slow, but this statement about the rate of a moving clock depends on how simultaneous times are compared along the clock's path. When observers compare rates, they implicitly use their own simultaneity slices to decide which reading of a moving clock corresponds to a given reading of their own clock. Because simultaneity differs between frames, naive comparisons can lead to apparent contradictions. Once the full Lorentz transformation is used, including both time dilation and the relativity of simultaneity, the description becomes consistent. Another misreading is to treat simultaneity as if it only affects distant clocks in empty space. It also appears in accelerated motion and in rotating frames, which are closer to everyday experience in vehicles and on planets. In an accelerating rocket, different parts of the rocket have different instantaneous inertial frames at each moment, and maintaining synchronized clocks along its length requires accounting for both acceleration and the finite speed of light. In a rotating frame like Earth, there is no global inertial frame covering the entire rotating platform. Synchronizing clocks around a closed loop on a rotating surface leads to a mismatch known as the Sagnac effect, where signals traveling in opposite directions around the loop return at different times. This is not because light changes its local speed. Locally, it still travels at the same speed. It is because the rotating frame's notion of simultaneity and time around the loop is not globally consistent in the same way as in an inertial frame. Modern navigation systems must correct for the Sagnac effect to maintain accuracy. The presence of such corrections in practical technology is another reminder that simultaneity is not a philosophical curiosity, but a structural feature of spacetime that matters when precision reaches a certain level. The relativity of simultaneity also clarifies the nature of causality. While simultaneity depends on frame causal order, does not for events that can be connected by signals travelling at or below the speed of light. If one event can influence another, the influence must travel within or on the light cone defined by the metric. All observers agree on that causal structure, even though they disagree on which distant events are simultaneous. The misreading to avoid is that relativity implies that cause and effect can flip arbitrarily. For events separated by a time-like interval meaning a signal slower than light could connect them, all observers agree on their order. For events separated by a space-like interval meaning no signal at or below light, speed can connect them. Different observers can disagree about which happens first, but because neither can influence the other, the disagreement does not create a physical contradiction. This is where the fabric is often misread. The mind wants a single global time order for everything, but the universe provides a consistent structure where only causally connected events have an invariant order. Cosmology introduces another layer. In the expanding universe model, a cosmic time coordinate is often defined for commoving observers who see the universe as homogeneous and isotropic. This can tempt a misreading that cosmic time restores an absolute simultaneity. Cosmic time is a useful coordinate for that specific class of observers, and that specific symmetry, not a universal time that all observers must accept. Observers moving relative to the cosmic frame still have their own local inertial frames and their own simultaneity conventions. The cosmic time slicing is convenient for describing the evolution of large-scale properties, but it does not negate the relativity of simultaneity in local physics. The practical lesson in this region is that time coordination is a procedure, not a metaphysical given. Synchronizing clocks across distance requires a convention and a physical method using signals. The chosen method works within the geometry of space-time, and different inertial motions lead to different consistent assignments of distance simultaneity. The fabric is misread when one insists that there must be a single true now that all observers share when disagreements in simultaneity are treated as observational mistakes rather than coordinate differences, or when the role of signal-based synchronization is ignored. Read carefully. Simultaneity becomes a steady feature of the same structure that produces time dilation. It is the reason the universe can keep a consistent causal order without granting a universal present, and it is the reason precise timekeeping across moving and rotating systems requires careful definitions rather than reliance on instinct. The inward step to extreme objects begins where density and compactness become high enough that the weak field approximations of everyday gravity no longer capture the dominant behavior, and where space-time curvature becomes the central feature rather than a small correction. Neutron stars and black holes are the clearest known arenas. They are not exotic merely because they are rare. They are extreme because they concentrate mass into small radii. Raising escape speeds to significant fractions of the speed of light, and producing strong gravitational time dilation, strong light bending, and in some cases measurable frame dragging. A common misreading is to treat these objects as ordinary bodies with unusually strong pulling power, as if gravity remains a simple force that scales up without changing its character. The corrected reading keeps the same underlying rule matter and energy shape the metric, and the metric shapes freefall paths and signal propagation. What changes is not the principle but the magnitude which makes effects that are negligible elsewhere become dominant. Neutron stars form when the core of a massive star collapses at the end of its life, and the collapse is halted not by ordinary gas pressure, but by quantum and nuclear physics. inner neutron star matter is compressed to densities comparable to those inside atomic nuclei. The star is typically only a few tens of kilometers in radius while containing more mass than the Sun. The interior structure is still an area of active research because the equation of state, the relationship between pressure and density at such extreme conditions, is not fully known. Different theoretical models predict different radii and different maximum masses, and observations aim to constrain these possibilities. Even without full certainty about the deepest interior, several facts are secure. The surface gravity is immense, so the gravitational redshift of light leaving the surface can be significant. The curvature is strong enough that time for a clock near the surface passes more slowly relative to a distant clock by an amount large enough to matter for interpreting signals. Light bending is strong, meaning that photons emitted from the surface can be redirected so that an observer can see more than half of the star's surface at once, depending on compactness. This is often misread as a strange visual trick, rather than a geometric consequence, the null geodesics near the star curve through the surrounding metric altering which surface patches can send photons to distant detectors. Neutron stars also spin rapidly. Many rotate dozens to hundreds of times per second. Rapid rotation and strong gravity together introduce frame dragging, where the rotating mass influences the local inertial frame, slightly twisting the spacetime around it. The effect is subtle compared with the gross curvature, yet it becomes measurable through precise timing and through the motion of matter in the surrounding accretion flow. Another misreading is to picture frame dragging as space being physically stirred like a fluid. The more accurate view is that the metric includes off-diagonal terms in appropriate coordinates that encode how time and angular coordinates mix, and this changes how free-falling objects and gyroscopes behave relative to distant stars. Around some neutron stars, matter from a companion star forms an accretion disk. As the matter spirals inward, it heats and emits X-rays. The observed variability and spectral features from these disks carry imprints of strong gravity, including gravitational redshift Doppler, boosting from high orbital speeds and light bending. In some systems, bright hot spots on the neutron star surface rotate in and out of view, producing pulses that are shaped by the star's compactness and by light bending. By modelling these pulses, observers infer constraints on mass and radius, and thus on the equation of state. This is another place where misreading can occur. The signals are complex, affected by magnetic fields, radiation transport, and geometric beaming, so no single modelling choice should be treated as final without uncertainty accounting. Yet the underlying logic remains that strong curvature leaves measurable signatures in timing and spectra. Magnetic fields in neutron stars can also be extraordinarily strong, especially in magnetars reaching levels where quantum electrodynamics modifies how light propagates through the magnetized vacuum near the star. These effects are not primarily gravitational, but they coexist with strong curvature and can complicate interpretations, reminding that extreme objects are multi-physics environments where gravity is dominant, but not alone. Black holes represent the next inward step in compactness, defined not by a material surface but by the presence of an event horizon, a boundary beyond which signals cannot reach distant observers. The simplest black hole in general relativity is described by a solution characterized only by mass, and if rotating by angular momentum with charge expected to be negligible in most astrophysical settings, because surrounding plasma neutralizes it. The event horizon is often misread as a physical surface or as a place where gravity becomes infinitely strong in the everyday sense. The horizon is not a material wall. It is a geometric boundary in space-time. A freely falling observer crossing it does not encounter a special local force at the crossing, assuming the black hole is sufficiently large that tidal forces at the horizon are mild. The dramatic features arise from the global causal structure once inside future directed paths that remain slower than or equal to light, cannot return to the outside region. Another misreading is to imagine that a black hole actively sucks in matter from afar. In reality, outside the horizon, the gravitational field can be similar to that of any object with the same mass, and whether matter falls in depends on its initial conditions, angular momentum and the presence of dissipative processes like collisions and radiation. Accretion disks form because matter usually has angular momentum and cannot fall straight in. It must lose angular momentum through friction-like processes and magnetic stresses before it can spiral inward. The strong gravity near the inner disk produces high orbital speeds and intense heating, making accreting black holes among the brightest X-ray sources. Observers infer black hole properties by modeling disk emission by timing variability and by measuring relativistically broadened spectral lines, all shaped by gravitational redshift and Doppler effects. The bending of light near a black hole can also produce multiple images and can focus emission from different disk regions toward a distant observer. In recent years, very long baseline radio observations have produced images of the bright ring-like structure around the shadow region of supermassive black holes in nearby galaxies. This ring is not the horizon itself. It is light from hot plasma that has been lensed by the strong gravity, with some photons orbiting the black hole one or more times before escaping. The misreading to avoid is that such an image is a direct photograph of a hole in space. It is an observation of emission, shaped by geodesics in a curved metric, and interpreting it requires modeling the plasma as well as the gravitational field. Time near black holes is another source of misreading. Distant observers often describe infalling matter as appearing to slow down and fade as it approaches the horizon due to gravitational redshift and the way coordinate time is assigned in certain coordinate systems. This can be misread as the claim that nothing ever crosses the horizon. In the proper time of the infalling matter, crossing occurs in a finite time, while signals sent outward become increasingly redshifted and delayed in arrival for distant observers. Both statements can coexist because they refer to different time coordinates and different operational comparisons. What remains invariant is the causal structure once inside no future directed signal reaches infinity. The strongest local effects near a black hole are not at the horizon, but closer to the central region where curvature grows and tidal forces can become large. In the classical description, the very center contains a singularity, where curvature scalars diverge, indicating the breakdown of the theory's applicability. This is not an invitation to treat the singularity as a literal physical point that is known to exist as described. It is an indication that general relativity as a classical theory is incomplete in that regime, and likely requires quantum gravitational physics to provide a consistent description. This is a careful boundary of knowledge. Horizons are well described by general relativity and are supported by many observations, while the nature of the central region is not directly observed, and is where theoretical expectations signal a need for deeper physics. Extreme objects also create and respond to gravitational waves. Compact binary systems of neutron stars and black holes lose orbital energy through gravitational radiation and in spiral. The waves carry information about masses and spins and about the dynamics of space-time in strong-field rapidly changing conditions. detected waveforms match general relativity's predictions remarkably well across many events. Neutron star mergers additionally produce electromagnetic signals and heavy element nucleosynthesis, offering a multi-messenger view that can test both gravity and matter physics. Misreading can arise when gravitational wave detections are treated as simple confirmations of black holes alone. They also probe the behavior of space-time under extreme curvature and the properties of dense matter when neutron stars are involved. Within this region, the fabric is misread when extreme gravity is imagined as a stronger version of ordinary pulling without geometric consequences, when event horizons are treated as hard surfaces, or as places where local physics must become instantly violent, when coordinate descriptions are confused with what an infalling clock measures, or when the singularity is treated as an established physical object rather than a signpost of theoretical limits. Read carefully, neutron stars and black holes show the same rule as the wider universe, but with the geometry turned up to a level where time dilation, light bending, frame dragging, and gravitational radiation are no longer quiet corrections. They become the main features by which the behavior of matter, light and clocks is understood in the deepest gravitational wells known in nature. The event horizon is an inward boundary in the geometry of a black hole, and it is often misread because it is defined not by what it is made of but by what it prevents. An event horizon is the surface that separates events that can send signals to distant observers from events that cannot, assuming the black hole persists into the future. It is a global causal definition. Whether a point in space-time lies inside the horizon depends on the entire future development of the space-time, not only on local conditions at that point. This global character is one reason horizons feel counterintuitive. People tend to look for a local marker, a place where gravity suddenly becomes infinite, or where matter hits a surface. In classical general relativity, there is no such local marker at the horizon for a freely falling observer, and gravity need not be infinite there. The local curvature at the horizon depends on the black hole's mass. For a stellar mass black hole, tidal forces near the horizon can be strong, but can still be survivable for a brief time. For a supermassive black hole, tidal forces at the horizon can be mild. The misreading to avoid is that the horizon is a special place in the sense of local physics. It is special in causal structure, not in immediate local sensation. Another misreading is to treat the horizon as the boundary of the black hole in a spatial sense, as if it were the surface of a sphere in ordinary space. The horizon is a null surface, meaning it is traced by light-like paths, and it is embedded in the full, four-dimensional space-time. Its location can be described in particular coordinate systems as a radius, but that description depends on coordinates and on the black hole's rotation and surroundings. In realistic astrophysical settings, black holes are not perfectly isolated. They are surrounded by accretion flows, magnetic fields, and sometimes by companions. Horizons in dynamic situations can change with time as mass and angular momentum fall in. The event horizon is distinct from the apparent horizon, a surface defined more locally by the behavior of outward directed light rays at a given time slice. In many situations, these horizons coincide or nearly coincide, but in dynamic spacetimes they can differ. The distinction matters in theory and in numerical simulations. The misreading arises when any detected boundary-like behavior is labeled an event horizon, without attention to the definition. Observations support the existence of horizons in the sense that many black hole candidates lack a luminous surface and show behaviors consistent with matter passing inward without a rebound. Yet the strict event horizon is not observed directly. It is inferred within a model that matches multiple lines of evidence. This is not weakness. It is how physics works when dealing with causal structures. The horizon is also where time and space are sometimes said to exchange roles, another phrase that can mislead. In the simplest non-rotating black hole metric described in Schwarzschild coordinates, the coordinate labelled time outside the horizon becomes space-like inside, and the coordinate labelled radius becomes time-like, meaning that decreasing radius is as unavoidable as moving forward in time for time-like paths. This coordinate statement captures an important truth about causal structure inside the horizon. All future directed time-like paths move towards smaller radius. Yet the exchange of roles phrasing can be misread as a claim that time literally becomes a distance, and distance becomes time. The correct reading is that the light cones tip inward relative to the radial direction. Outside the horizon there exist future-directed paths that move outward, allowing escape. At the horizon, the outward light rays hover. Inside, even light directed outward still moves inward in terms of decreasing radius because the geometry constrains the causal directions. This is about the arrangement of allowed directions in space-time, not about a mystical swapping of dimensions. Another central misreading concerns the view from far away. In certain coordinate descriptions, an infalling object appears to slow and never cross the horizon, fading as its light is increasingly redshifted and delayed. This is a coordinate effect coupled with the practical reality that signals from near the horizon become harder and harder to receive. The object does cross in its own proper time, and nothing in classical general relativity prevents it. The distant description is not a lie. It describes what distant observers receive. The misreading is to take it as implying that the object is physically frozen at the horizon. The correct reading is that the horizon is a causal boundary. Once the object crosses, signals emitted afterward do not reach the distant observer. Signals emitted just before crossing can reach the observer, but are increasingly redshifted and time-stretched. In practice, astrophysical accretion disks are turbulent and emit radiation from a range of radii. The observable cutoff in emission is associated with the innermost stable circular orbit and with the plunge region, not with a bright surface at the horizon. For rotating black holes, the picture includes the ergosphere, a region outside the horizon, where frame dragging is so strong that no observer can remain at rest relative to distant stars. In the ergosphere, energy extraction processes are possible in principle, such as the Penrose process, and in magnetized accretion flows, a related electromagnetic mechanism can power relativistic jets. Misreading can occur when jets are attributed to the horizon acting like a nozzle. Jets are produced by a complex interaction of rotation, magnetic fields, and accretion. The horizon plays a role insofar as it is part of the rotating space-time and can support certain boundary conditions for fields, but the luminous and dynamical jet structure arises in the plasma outside. Another misreading is that a black hole's rotation drags all space around it like a whirlpool. Frame dragging is real, but its measurable consequences depend on distance and on the distribution of matter, and it is described by the metric structure rather than by a literal fluid motion. The horizon also intersects with thermodynamics in a way that deepens the sense that space-time is being misread when treated too literally. Classical general relativity suggests that a horizon's area cannot decrease in ordinary processes, a statement that resembles a second law. When quantum effects are included, black holes are predicted to emit thermal radiation leading to the idea of black hole temperature and entropy proportional to horizon area. This is not purely speculative fantasy. It emerges from semi-classical calculations that treat quantum fields on a curved background. However, direct detection of Hawking radiation from astrophysical black holes is far beyond current observational capability because the temperature for stellar mass and larger black holes is extremely low compared with cosmic background temperatures. The misreading to avoid is to treat black holes as glowing furnaces in space. In the observable universe, any radiation associated with accretion dominates completely, and Hawking radiation remains a theoretical prediction awaiting indirect support rather than a measured astrophysical signal. Yet the theoretical implications are significant because they connect horizons, quantum fields, and information in a way that exposes the limits of current understanding. This leads to the information puzzle, a question about how information about matter that falls into a black hole is accounted for if the black hole evaporates. The puzzle is not that physics is free to be inconsistent. It is that combining quantum theory, which is unitary and standard formulations, with classical notions of horizons and evaporation produces tension. Many proposed resolutions exist involving subtle correlations in radiation modifications near the horizon, or new ideas about how space-time is encoded. None is universally accepted as the final story, and this uncertainty must be stated without speculation beyond what is supported. The horizon then sits at the boundary between well-tested classical geometry and the region where quantum theory likely demands a deeper account. Another important inward concept is that horizons are observer-dependent in a broader sense. An accelerating observer in flat spacetime experiences a Rindler horizon, a boundary beyond which events cannot influence them due to their acceleration, and such horizons have thermal properties in quantum field theory. This can be misread as claiming that any observer can conjure a horizon, and therefore black hole horizons are not real. The correct reading is that horizons can arise from different causal structures, and their physical implications depend on the observer's world line and on the global space-time. Black hole horizons are not created by choosing a viewpoint. They are tied to the geometry produced by gravitational collapse and to the causal structure for distant observers. Yet the existence of horizon-like boundaries in other contexts shows that horizons are fundamentally about causal accessibility, not about material surfaces. At this inward step, the fabric is misread when the horizon is treated as a solid boundary, when coordinate-dependent appearances are treated as physical freezing, when phrases about time and space swapping are taken literally, or when quantum ideas about black hole radiation are projected onto astrophysical observations without scale awareness. Read carefully. The horizon is a precise geometric boundary that reorganizes causality, shapes the behavior of light and matter through the tipping of light cones, and points toward deeper questions where classical geometry and quantum theory meet. Not because the horizon is a dramatic place to touch, but because it is where the definition of what can be seen and what can be returned becomes part of the structure of space-time itself. The inward step to quantum series begins where the smooth geometric picture of space-time, so effective from galaxies down to event horizons, is expected to be incomplete. General relativity treats space-time as a differentiable manifold with a metric that can vary smoothly. Quantum theory treats matter and fields as having intrinsic uncertainties and discrete features in their interactions. When these frameworks are applied together, they work well in many regimes through quantum field theory on curved space-time, where quantum fields propagate on a classical geometric background. This hybrid approach predicts effects such as particle creation in expanding universes and the thermal properties associated with horizons. Yet it does not provide a complete account when the curvature itself becomes subject to quantum uncertainty, or when energies and densities approach the scale where quantum gravitational effects are expected to dominate. This region is where the fabric is most easily misread because everyday language pushes toward pictures of space-time made of tiny tiles or threads, while the actual state of knowledge is careful and constrained. What is firmly known is that the two successful theories as currently formulated are not fully unified, and that the regimes where both are simultaneously crucial include the very early universe and the deep interior regions associated with classical singularities. Another secure point is that any quantum theory of gravity must reproduce general relativity as an effective description at large scales, and must reproduce quantum theory in the appropriate limits. Beyond that, much remains uncertain, and it is important to state uncertainty without inventing details. A key concept that motivates the need for new physics is the Planck scale, derived from combining the gravitational constant, the speed of light, and Planck's constant. At lengths near the Planck length and times near the Planck time, dimensional analysis suggests that quantum fluctuations of geometry could become significant. This does not mean that space-time is proven to be granular at that scale. It means that the naive application of classical geometry and of standard quantum field theory may break down and new degrees of freedom or new principles may be needed. Another motivator is the presence of singularities in classical general relativity, where certain curvature invariants diverge and geodesics end. The prevailing expectation is that singularities indicate the breakdown of the classical theory, rather than the existence of literal infinite curvature in nature. Yet this expectation is not a direct observation. It is an inference drawn from the pattern of how physics has behaved in the past, when infinities appear in effective descriptions. Quantum electrodynamics, for example, handles certain divergences through renormalization, and many divergences in classical descriptions correspond to regimes where new physics appears. This historical pattern guides the expectation that quantum gravity resolves classical singularities, but the specific mechanism is not settled. One misreading in this region is the claim that quantum uncertainty must make space-time foam-like in a literal frothing sense, with tiny black holes popping in and out of existence. Some heuristic arguments and semi-classical pictures use such language, but they are not established descriptions. They serve as intuition for why classical geometry might fail at very small scales. A disciplined reading keeps the distinction between metaphor and tested statement. Another misreading is to treat the Planck scale as a boundary that can never be probed. Direct probing at that scale by particle accelerators is far beyond current technological reach, but indirect constraints may exist. For example, if space-time discreteness or Lorentz symmetry violation produced energy-dependent speeds of light, high-energy photons from distant astrophysical sources could arrive with measurable delays relative to lower-energy photons. Observations have placed strong constraints on such effects, though interpreting them requires caution because source emission processes can also create delays. Similarly, quantum gravity might leave imprints in the early universe that affect the statistics of cosmic microwave background fluctuations or primordial gravitational waves. Present data constrain many possibilities, but no decisive unique signature has been confirmed. This uncertainty is essential. There is no single experimentally established theory of quantum gravity at present. Several approaches exist, One approach is string theory, which replaces point particles with extended objects and requires additional dimensions in its consistent formulations. In this view, gravity arises from a quantum excitation of the string, and the theory provides a framework that can be finite in regimes where naive quantum gravity would diverge. Another approach is loop quantum gravity, which attempts to quantize geometry directly leading to discrete spectra for certain geometric operators such as area and volume in its formalism. There are also approaches based on causal sets, asymptotic safety, emergent gravity ideas, and others. Each has technical successes and open problems. It would be a misreading to present anyone as established truth. The careful statement is that these are active research programs aiming to produce a consistent quantum description of space-time, and that none has yet achieved broad empirical confirmation. The most concrete bridge between quantum theory and space-time geometry remains semi-classical gravity, where quantum fields live on curved backgrounds. In this framework, particle creation in expanding space-time is a robust prediction. A field mode that begins in a vacuum state at early times can evolve into a state that contains particles at later times, because the notion of vacuum depends on how modes are defined, and mode definitions depend on the time evolution of the metric. This is not a claim that particles are created from nothing in a mystical sense. It is a statement that the decomposition of a quantum field into particle excitations is observer and time-dependent in curved or time-dependent backgrounds. The same framework predicts Hawking radiation from black holes and Unruh radiation for accelerating observers. These predictions have consistent mathematical structure, but only some related effects have experimental analogues in laboratory systems, and the astrophysical Hawking signal remains unobserved directly. Another misreading is to treat these effects as optional interpretations. In the framework where they are derived, they are necessary consequences, though the framework itself might be modified by a full quantum gravity theory. The information puzzle sits at the center of why this region matters. If black holes can evaporate and disappear, and if the radiation is purely thermal with no information, then quantum evolution would appear non-unitary. Many researchers expect that unitarity is preserved and that information is encoded in subtle correlations in the radiation, perhaps through quantum entanglement structures that connect the interior and exterior descriptions. Yet how this encoding coexists with the equivalence principle and with the smoothness of the horizon for infalling observers is the core of the tension. Proposed ideas include black hole complementarity holography and the notion that space-time geometry might emerge from patterns of entanglement. The holographic principle motivated by black hole thermodynamics and by results in certain quantum gravity models suggests that the information content of a region can scale with its boundary area rather than its volume. In some contexts, particularly in the ADS-CFT correspondence, there is a precise mathematical realization of holography. However, applying these insights to the universe as a whole and to realistic cosmological settings remains an active area, and it would be a misreading to claim that holography has already fully explained space-time. It provides a powerful set of clues and tools, not a closed story. The early universe is another place where quantum space-time questions arise. Inflation, a proposed period of rapid accelerated expansion in the early universe, is supported indirectly by the near scale. Invariant spectrum of primordial fluctuations seen in the cosmic microwave background. In the standard account, quantum fluctuations of fields during inflation are stretched to cosmic scales and become the seeds of structure. This is a remarkable linkage between quantum physics and the large-scale universe, but it still operates within a semi-classical framework where the background space-time is treated classically. A full quantum gravitational treatment of the very earliest moments, possibly including a pre-inflationary phase or a bounce scenario in some models, is not settled. Observationally, the search for primordial gravitational waves in cosmic microwave background polarization continues to constrain inflation models, but no definitive detection of the relevant primordial signal has been confirmed. Thus, while quantum fluctuations likely play a role in the origin of large-scale structure, the deepest description of the earliest time remains uncertain. At this inward step, the fabric is misread when speculative imagery is treated as fact. When one research approach is presented as settled, or when the Planck scale is treated as a magical boundary rather than a practical indicator of where current theories may fail. Read carefully, the quantum scale region is defined by what is known to be incomplete, and by where multiple consistent frameworks point toward new principles. It is characterized by robust semi-classical predictions in certain regimes, by strong theoretical motivations from singularities and horizons, and by ongoing efforts to build and test a quantum theory of geometry. The calm conclusion inside this region is not a final claim about what spacetime is made of. It is the measured acknowledgement that the smooth fabric is an effective description across a vast range, and that at the smallest scales the correct description is still being sought, guided by consistency requirements and by the limited but growing set of observational constraints. The final inward region is not a new place with a mapped boundary, but a set of open questions that sit at the deepest layer of the current reading of space-time. These questions persist because the existing frameworks, general relativity and quantum theory, each work extraordinarily well in their own domains, yet they do not merge into a single account that can be applied without tension in regimes where both must matter. It is tempting to treat these open questions as gaps that will soon be filled with one neat answer, or as mysteries that allow any speculation. Both are misreadings. The careful view is that the questions are constrained by what is already measured, and that progress is made by building theories that are mathematically consistent, that reproduce established results, and that offer testable consequences. The deepest questions can be grouped by theme without turning them into a list of claims, keeping them as a continuous exploration of what remains uncertain. One central question concerns whether space-time as described by a smooth manifold and metric is fundamental or emergent. In many areas of physics, effective descriptions emerge from deeper microscopic rules. Fluids have a smooth velocity field description that emerges from molecular motion. Solids have elastic properties that emerge from atomic structure. It is natural to ask whether the smooth geometry of spacetime is similarly emergent from deeper degrees of freedom, perhaps quantum and informational in character. Some theoretical results, including aspects of holography and entanglement-based reconstructions of geometry, in specific models, suggest that geometry might be closely linked to quantum correlations. Yet it is not settled whether this represents a universal principle or a feature of certain special theories and boundary conditions. The misreading to avoid is to treat emergence as a proven replacement for geometry. It remains a promising direction supported by partial insights, not a completed account. Another deep question concerns the nature of the gravitational field in quantum terms. In ordinary quantum field theory, fields have quanta, and interactions can be described by particle exchange in appropriate regimes. Gravity is expected to have a quantum carrier often called the graviton in perturbative approaches, but a full non-perturbative definition of quantum gravity is not established in general settings. In weak gravitational fields, treating gravity as a quantum field on an almost flat background can be useful and internally consistent at low energies. But this approach runs into difficulties at high energies where perturbation theory breaks down. The misreading is to think that the graviton concept by itself solves quantum gravity, or that the failure of perturbation theory implies gravity cannot be quantized. The more accurate statement is that the standard perturbative method is insufficient and that a deeper framework is required. A related question is whether space-time at very small scales has discrete structure. Some approaches predict discrete spectra for geometric quantities, while others maintain continuous structure but modify the dynamics. Present observations have not confirmed any discreteness. Constraints on Lorentz invariance violation and on energy-dependent propagation are strong, suggesting that if discreteness exists, it either respects Lorentz symmetry in a subtle way, or appears only through effects too small to detect with current methods. Misreading arises when discreteness is presented as a certainty because it feels intuitively modern. The correct reading is that discreteness is a proposal with partial theoretical motivations and no definitive empirical confirmation. A further question concerns singularities. Classical general relativity predicts singularities inside black holes and in the early universe under broad conditions, with theorems showing geodesic incompleteness when certain energy conditions and global assumptions hold. The theorems do not describe the detailed nature of singularities, and they do not include quantum effects. Most physicists expect that quantum gravity resolves singularities, replacing them with a different structure, perhaps a bounce, perhaps a high curvature region with new degrees of freedom, perhaps a transition to another phase. The misreading is to claim that singularities are either literal points of infinite density known to exist, or that they are automatically removed in any plausible quantum theory. Both are too strong. The careful statement is that classical singularities indicate the breakdown of the classical description, and resolving them is a key requirement for a successful deeper theory. Another deep question concerns the information problem and the consistency of black hole evaporation with quantum unitarity. Semi-classical reasoning suggests black holes radiate thermally and can lose mass, but thermal radiation appears to carry little information about the initial state. If a black hole disappears completely, a pure quantum state could evolve into a mixed state which standard quantum theory forbids. Many proposals suggest that the information is not lost, but encoded in correlations among the radiation quanta in a way that becomes visible only when considering the full quantum state, not just the thermal spectrum. The holographic principle and results in controlled model systems support the idea that unitarity can be preserved, but translating those insights into a fully intuitive space-time picture that also preserves the equivalence principle for infalling observers remains challenging. Misreading occurs when any one proposed resolution is taken as final, or when the problem is dismissed as only philosophical. It is a consistency question at the heart of how quantum theory and space-time coexist. Another open question is the nature of dark energy and cosmic acceleration. Observations indicate that the expansion of the universe is accelerating at late times, and the simplest explanation within general relativity is a cosmological constant, a constant energy density of the vacuum. Yet the observed value is extraordinarily small compared with naive estimates of vacuum energy from quantum field theory creating the cosmological constant problem. Alternatives include dynamic fields that evolve over time, modifications of gravity on large scales, or subtle observational and modelling systematics. Current data strongly constrain many alternatives, and the cosmological constant remains consistent with observations, but the deep origin of its value is unknown. The misreading here is to treat dark energy as a known substance with identified particles, or to treat the smallness problem as mere numerology, is a profound gap between theory expectations and measured reality. Another intertwined question is the nature of dark matter. The evidence for unseen mass is strong across many scales, from galaxies to the cosmic microwave background and large-scale structure. Yet the microscopic identity of dark matter has not been confirmed. Candidates range from weakly interacting massive particles to action-like particles to other possibilities, and there are also proposals that modify gravity instead of adding dark matter. Many observational and laboratory searches have constrained broad classes of models, but no definitive detection has been made. The misreading is to assume that because the gravitational evidence is strong, the particle identity is already known. It is not. This uncertainty matters because the behavior of dark matter at small scales can influence galaxy formation, and thus the detailed reading of space-time curvature in the universe. Another deep question lies in the precise value of the current expansion rate known as the Hubble constant, and the tension between different methods of measuring it. Early universe inference, using the cosmic microwave background within the standard model, yields one value, while late universe distance ladder measurements yield another. If the tension is not due to unaccounted systematics, it could indicate new physics, such as additional energy components in the early universe or modified interactions. The situation is active and not resolved. So the misreading to avoid is to treat the tension as either a settled discovery of new physics or as a trivial measurement error. It is a persistent discrepancy that is being tested by improved measurements and cross-checks. There are also open questions about gravity itself. General relativity has passed many tests, including strong field tests from gravitational waves, yet there remain regimes where it is not tested directly, and there remain theoretical reasons to consider possible modifications, especially when trying to unify gravity with quantum theory or to explain cosmic acceleration. Any modification must reduce to general relativity where it is well tested. Misreading occurs when modifications are proposed without respecting this constraint, or when any anomaly is immediately attributed to new gravity, rather than to complex astrophysics or measurement systematics. At the deepest layer, there is also the question of time. In quantum gravity, time can appear differently, because in general relativity time is part of the dynamical geometry, while in standard quantum mechanics time is an external parameter. Reconciling these roles leads to the so-called problem of time in canonical approaches, where the equations can appear to lack a time evolution in the usual sense. Some approaches address this by defining relational time using one physical degree of freedom as a clock relative to others. This is technically intricate and not resolved. The misreading is to interpret this as suggesting that time is an illusion. The more accurate statement is that defining time evolution in a theory where geometry is quantum and dynamical is non-trivial, and different formulations handle it in different ways. Finally, there is the question of what observations can reach. New gravitational wave detectors, more precise cosmological surveys, improved pulsar timing arrays, and continued particle searches may tighten constraints and reveal new clues. Yet the deepest scales may remain indirectly accessible, requiring inference rather than direct probing. This is not a weakness but a realistic boundary of measurement. The correct reading of the fabric at this inward edge is therefore disciplined. It holds on to what is solid, the success of general relativity across vast scales, the success of quantum theory in its domain, the robust semi-classical links between fields and curved backgrounds, and the strong observational evidence for dark matter and cosmic acceleration. It also holds on to what is genuinely unknown, the microscopic nature of dark components, the quantum structure of geometry, the resolution of singularities, and the reconciliation of horizons with unitarity and with the lived smoothness implied by the equivalence principle. These are open questions not because the universe is being mysterious on purpose, but because the current reading tools, though powerful, are not yet complete at the deepest layer. The inward journey settles into stillness as the questions fade from active edges into a quiet background. Space-time read from its widest sweep to its deepest uncertainties does not resolve into a single image or metaphor. It remains a set of measured relations that hold steady across scales, even as the language used to describe them shifts. Expansion becomes local motion. Curvature becomes weight. Time becomes something counted by clocks rather than assumed. At each layer, misreadings fall away not through drama, but through careful comparison of what is measured with what is inferred. The universe does not announce its structure. It allows itself to be read slowly through light that travels long paths through clocks that accumulate time differently through matter that moves where geometry permits. Near the surface of daily experience, space-time feels simple because the differences are small. Deeper in near compact objects or early epochs, the same rules apply with greater intensity. There is no sudden change of law, only a change of scale. What remains consistent is that space and time are not passive stages. They participate, they respond, they constrain what can happen and how it can be known. Where knowledge ends, it does not end in mystery but in careful silence marked by boundaries that current tools cannot cross. The fabric is misread when it is treated as substance as illusion or as metaphor alone. It is also misread when uncertainty is mistaken for freedom to invent. The quieter reading accepts limits without closing inquiry. It allows space-time to be what the evidence supports at each scale, no more and no less. The result is not a conclusion, but a steady resting place where motion slows, distinction soften, and the mind is no longer required to resolve every question. The universe continues. Geometry holds, time accumulates, light moves on. There is nothing further to extract, only the calm persistence of relations unfolding without urgency, inviting rest rather than interpretation.